Hello everyone. Tonight we're going to dive into the secrets of matter. This long talk is going to be about physics, but physics understandable by everyone. You will be able to follow whatever knowledge you have in that field. So I have put together a discovery journey of various aspects of matter. It will start with what we are made of, what our bodies are made of. And then we will jump scale several times toward the infinitely small, from our biological tissues to molecules, to atoms, to the particles atoms are made of, and the nature of these particles. In the second part, I will tell you about nuclear fusion, a good opportunity to take a look at the physical forces that rule over matter. And an illustration of some of them is what happens when the nuclei of atoms merge, fuse. We are not there yet, but nuclear fusion could one day become a source of abundant and cheap energy. I will also tell you why and how this could be achieved. After that, in part 3, we will jump from this microscopic scale to the cosmos and explore historical and modern theories about the nature of the universe, where the center of the universe could be, if there is one, and the main theory about the first moments of our universe, the Big Bang theory. And finally, in the fourth and last part, we will travel through space, looking at different objects, different phenomena that illustrate all this. Stars and their life cycles, neutron stars, black holes, or the mysterious dark matter, and other questions that remain unanswered at this point. This will be long and touch on many topics. But as I said, it is all going to be accessible as long as you take your time, relax, and let me do the work. There are timestamps to help you navigate between the many chapters, and as always, I invite you to support this channel on Patreon if you wish to. This is what keeps it active, free of ad breaks and without sponsorships. And now, let's get started with our first part, a dive to the infinitely small. What is matter? This is a trickier question than it seems, because a possible answer to the question is that matter is the substance the physical universe is made of. It takes up space by having volume, and it has mass. This is how matter is defined in chemistry or in classical physics, and it matches our perception in everyday life. We are surrounded by matter, objects that can be touched, furniture, walls, vehicles, all sorts of accessories and devices. We know we breathe in an atmosphere made of gas, which is just less dense matter. And from water to air to nature, everything that physically surrounds us is matter. As you know, the little bricks this matter is made of are called atoms. But it could be more complicated than that, because the atomic scale is far from being the smallest that we know of. We'll see later in our exploration that atoms are a combination of particles which themselves are made of even smaller components. Don't think too much about this yet, but we'll see that these components can be massless and not have any size, which defies our perception of what the physical world is made of. There are particles like photons, the particles of light, that exist without having any mass. There are waves too, like sound, which are phenomena. They are very much a part of the physical world, but they are not matter. Except that we'll see at the end of the story that the tiny constituents of matter can behave like waves. This means that matter is actually hard to define once and for all. Its definition depends a lot on which scale we position ourselves, and several levels, several scales are possible. We're going to dig into this, starting from the everyday usage which defines matter as atoms and anything made up of them. And then we will dig deeper at various subatomic levels and discover a world where the laws of physics diverge greatly from what we are accustomed to. I told you at the beginning that we would explore what we are made of. So our first step in our journey to the infinitely small is going to be the cell. Cells are the basic biological units of all known living organisms. The basic understanding of the architecture of living organisms dates back from the 17th century, which is also the century when the first modern microscopes were invented. Prior to that, there were lenses to magnify things. They appeared in the antiquity, but in the Middle Ages, in the 13th century, simple microscopes that were just magnifying glasses were invented. And this is when the exploration of the microscopic world really began. These very basic microscopes were far from powerful enough to see things at the cellular level. To be able to see even smaller things, compound microscopes were invented in the 17th century. They combined a lens near the specimen observed and an eyepiece to view a real image. They were perfected along the century, adding better lighting in particular, and by the end of it, the first discoveries in microbiology took place. The existence of blood cells and the first descriptions of living tissues. In biology, the concept of tissue was introduced 2 centuries ago, when it was understood that organs, internal like our hearts, our lungs, or our brains, or external like skin, were not entities in themselves, with the same cellular structure repeated over and over again. They were made of different types of structures, called tissues, that carry out a specific function. In the bodies of animals, in biology that includes human beings, some tissues protect an organ from the outside, They cover its surface and act as a barrier. There are also connective tissues that are found in between other tissues everywhere in the body. They support and protect it. For example, they include collagenous fibers that bind the bones and other tissues to each other, or elastic fibers that allow our lungs to recoil. We also have muscular tissue that can contract to produce force and motion, and nervous tissue that is the main component of the nervous system. Without exception, all these tissues are made of cells with different sizes and properties that work together. But living cells are very diverse too. On Earth, we know of two types of cells. The oldest type are called prokaryotes. These cells are the most ancient forms of life that we know of on Earth, and some of them found fossilized were dated to 3.5 billion years ago. Prokaryotes do not bond to form large multicellular organisms. They are unicellular beings. Bacteria are prokaryotes, for example, and their cell is quite different from the ones that constitute our bodies. There are various shapes of prokaryotic cells. They can be spherical or ovoid. In that case, they are called cocci. They can be cylindrical, bacilli, or in spiral, and there are more. But there is always one single cell in these organisms, with a wall, an outer covering that protects the cell and gives it shape. Then there is a membrane that regulates the flow of substances in and out of the cell. And inside, there is a part called cytoplasm. This is a gel-like substance in which various components are enclosed. There are compounds to assimilate organic molecules called enzymes. Enzymes are biological catalysts. They accelerate chemical reactions, and the cell uses these chemical reactions to convert organic molecules into different molecules. This process liberates energy that the cell can use and building blocks. Another part of the cytoplasm that takes a lot of space within the cell is called the nucleoid. It is the region of the cell that contains its genetic material, DNA. We'll see a bit further what DNA actually is. Prokaryotes are very small, obviously, to our scale, but they are giants if we start counting the atoms and molecules they contain. They have millions of molecules. I told you there were two kinds of cells. Prokaryotes are one type. The other is eukaryotes, which are the building blocks of all plants, animals, or fungi. Eukaryotes are more complex and a lot bigger. They can be as much as 1,000 times greater in volume than prokaryotes. It is believed, based on fossil records, that eukaryotes appeared after prokaryotes, and it makes sense if we take into account the difference in size and complexity. there is still an open debate today about whether the existing prokaryotes in our environment are directly descending from the first prokaryote, or whether they re-evolved from eukaryotic cells. In any case, the main difference between the two types, apart from the size, is that eukaryotes have compartments inside. Specific activities take place in different compartments of the cell. One of these compartments is the cell's nucleus. Instead of occupying a region of the cell in which it floats inside the cytoplasm, like in prokaryotes, the genetic material is enclosed in a nucleus in eukaryotes and separate from the rest, for the most part, because there are also other small compartments called mitochondria that also contain some DNA, but not chromosomes. We'll come back to the distinction later. However small, an eukaryote may contain billions and billions of molecules. It's a small world in itself. Eukaryotic cells also contain big molecular machines called ribosomes that perform synthesis of other molecules. In plants and algae, they have compartments that perform photosynthesis and can capture the energy from sunlight. And contrary to prokaryotes, they have the property to form colonies or multicellular organisms with specialized cells. Every single second in our bodies, even when we stay still or when we're asleep, billions of chemical and mechanical reactions in our cells are taking place, ensuring that our organisms stay biologically alive. Cells move, they repair, they transport, and they multiply, they replicate. This is where DNA matters. New cells appear by division. One single mother cell divides into two daughter cells, which are copies of the original one. This is what allows growth in multicellular organisms like us, and also the replacement of cells when they die. Human cells, for example, are specialized because we are complex organisms and they have very different lifespans. White blood cells live for only a few days and need to be replaced quickly. Skin cells in the top layer of our skin live about a month. Red blood cells that transport oxygen about 4 months. Liver cells 18 months. And there are some, like in the middle of our eye lenses, that last our entire life. On average, the cells in our bodies are entirely replaced every 7 to 10 years. And it is fascinating because when you meet someone again, after several years of separation, you're going to talk to the same person, but 99% of the stack of matter you have in front of you has changed. It has been renewed. It is obviously the same person with a conscience, memories, a history. Believers will say the same soul, and biologically it is the same organism, but the matter has been almost entirely changed. Replicating a cell and 4 multicellular organisms, coding the entire architecture of the body with its parts, its functions, and how they interact. This requires information. This is where DNA matters, genetic information. DNA is a molecule, but a very big one. These very large and complex molecules are called macromolecules. Under the microscope, it looks like a double helix, two spirals that coil around each other and contain genetic instructions for the development, functioning, and reproduction of all known organisms. The process is very complex, but a comparison could be made with binary language, like the one used in computers. Except instead of having two signals, 0 and 1, there are 4. The DNA molecule is a long sequence of building blocks that come in 4 different types. They are called by letters A, T, C, and G. And instead of being an electrical signal, like in electronics, it is via chemical reactions that information is put to use. Certain proteins will bond with DNA, and they will react to the sequence of building blocks. This is how they read the information enclosed in the DNA sequence. The concept is fairly simple. Protein molecules are attracted to the DNA, and they read and interact with the nearby sequence. It is biochemistry. But in practice, these interactions are extraordinarily complex. The DNA sequence is very long because it contains a lot of information. The process involves many different chemical reactions, and the complexity of what happens all the time in a single cell around DNA is mind-blowing. And to make things even more complex, there is also a bit of simpler DNA outside the nucleus in these compartments called mitochondria that also interact with molecules within the cell. What we call a chromosome is one DNA molecule because there are several in each cell. Their number varies between species, be they of plants or animals. Humans have 46 chromosomes, cats have 38, dogs 78. It is not necessarily an indicator of the complexity of the organism. For example, a goldfish has 100 chromosomes. In the DNA molecule, the two spiral chains of atoms that coil around each other are identical. They have the same structure and they carry the same information. When a cell divides, this is a process called mitosis. DNA replicates itself. The instructions to do that are part of the information it carries. A second nucleus appears and separates itself with part of the cell. After that, each new cell will grow until it is as big as the original mother cell. And genetically they are exact copies of it. But DNA also contains information to make different cells, in the case of multicellular organisms, in which cells are specialized. An embryo begins with one single cell. In the case of sexual reproduction, This single cell contains genetic information, genetic material from two individuals. And this information is unique to the future new one. This single cell divides into 2, then 4, then 8, then 16, and so on. And along the embryo's growth process, the activation of information coded in DNA makes new types of cells appear. They form specialized tissues and organs following an architecture that is also encrypted, coded into the chromosomes. Between the initial cell and a human body at birth, the size of the organism will be multiplied by billions and billions. But all the information required for this was already enclosed inside the very first cell. There would be many more things to say about microbiology, and maybe we will return to this in another story. But for now, let's continue our exploration of what we are made of and jump to another level. We saw that tissues were made of billions of cells, which are made of billions of molecules. So let's take a look at the molecular and atomic level. You know what atoms are. They are the smallest unit that defines an element. And as you also know, they contain various particles, protons, neutrons, electrons. In nature, atoms often have a tendency to regroup with other atoms of the same type or different. I referred a lot to molecules until now. Molecules are one such form of grouping between atoms, but they are not the only one. Molecules are very abundant in our biosphere. They make up most of the oceans, of the atmosphere, of our bodies and organic substances in general. They are also common near the surface of other planets in space. But it doesn't mean the appearance of molecules is a rule. It depends on the types of atoms and on the environment. Actually, the majority of solid substances on Earth, that includes most of the minerals that make up the planet from the crust to the core, are not made of identifiable molecules. To understand how all this works, we need to talk about atoms and something called electric charge. You are certainly familiar with the structure of atoms. They are composed of a nucleus and one or more electrons bound to it. The nucleus is an aggregate of two kinds of particles, protons and neutrons. Protons and neutrons are much more massive than electrons. More than 99.9% of the mass of an atom is in the nucleus. And as you also know, electrons and protons are said to be electrically charged. Protons have a positive electric charge and electrons a negative one. Neutrons have no charge. When an atom has the same number of protons and electrons, then it is electrically neutral. If an atom has more protons than electrons, or fewer, then it has an overall positive or negative charge, these atoms with an overall electric charge are what is called ions. But what is electric charge? It can be confusing because the word electric makes us think of electric current, electric power. And electric current is related to this. As you know, what we call electricity, the energy that powers a lot of devices, is a flow of matter, a flow of particles, electrons generally, but not always. And this flow moves from one point to another. These particles in motion energize equipment, from light bulbs to computers, motors, radiators. All the electric appliances we use transform the energy from electric current into light or heat or motion. But electric current exists because of electric charge. So forget about what we call electricity and think of it as a fundamental property of matter. Electric charge and electric current can be compared with mass and gravitation. As you know, all objects in the universe that have mass attract each other. The force is called gravitation, and it is the force that keeps galaxies and star systems together, or that gives us weight when we are on Earth because the planet's mass attracts us, attracts our bodies. Electric charge is another fundamental property of matter. It is a notion, like mass, that explains physical phenomena, except that mass is always positive, when electric charge can have two forms. They're called positive and negative because they appear opposed. When two objects with both a positive or both a negative overall charge are close, they tend to repel each other, whereas they will attract each other if their charges are opposite. This is the phenomenon called electromagnetism. Let's take a concrete example that we experience every day. For example, when we turn on the light. Electric current happens between 2 points because one has an excess of electrons. It is negatively charged, and another has a deficit. It is positively charged. If there is a bridge between these 2 points, like a wire, inside which electrons can move easily, the different potentials between the 2 points will tend to even. Electrons will move from one point to the other, and their motion is the force that powers the light bulb. When the light is switched off, the bridge, the circuit, is cut off. Current cannot materialize. When you push a button to turn on the light, or to turn on any electric appliance, what you do is move a little piece inside that closes the circuit and let the electrons flow. Of course, for the electricity to keep flowing, it is necessary to maintain a constant difference in potential, which is what a power plant or a battery does. So, like gravitation, electromagnetism is the force or the interaction that results from electric charge. It is one of the fundamental interactions that we know of, and that cannot be reduced to more basic interactions. It just exists as a fundamental property of matter. You may have heard of the four fundamental interactions or the four fundamental forces of physics. Gravitation and electromagnetism are two of them. They are the most obvious because they produce effects that can be seen directly in everyday life. There are two more that produce forces at a much smaller scale inside atoms. They are called the strong and weak interactions. We will come back to them later when we explore inside atoms. Maybe there are more than four. Some scientists suppose that maybe a fifth force might exist. Or perhaps there are four manifestations of another thing, another reality, something else that we don't understand at this point, or are unable to define. These four fundamental interactions are not laws set in stone, but in the current state of physics, they have been researched and quantified, and they work. They help make predictions about the behavior of matter, and these predictions have been verified from very large-scale objects like galaxies to much smaller scales like inside atoms. So I was telling you about electric charge to explain the formation of molecules. Around the nucleus, electrons revolve at high speed on one or several layers, one or several orbits. These orbits are called electron shells, and each shell can only contain a certain number of electrons. The first shell can hold up to 2 electrons, the second shell up to 8, the third up to 18, and so on. For reasons that have to do with energy levels that we will leave on the side for tonight, atoms like, with quotation marks, they like to saturate their outer shell because it gives them more stability. So atoms have a propensity to bond with other atoms and form molecules because sharing their electrons in pairs gives them this stability. For many molecules, the sharing of electrons between atoms allows each atom to attain the equivalent of a full outer shell. A simple example of this is with hydrogen. Hydrogen is the simplest of atoms. It has one proton in the nucleus and one electron. Ideally, 2 electrons would be more stable to fill in the first electron shell that can hold 2. So, in nature, 2 atoms of hydrogen will tend to bond and form one molecule where each atom has the equivalent of a full shell. The same happens with oxygen, but atoms of different elements can also bond. It is the structure of their electronic layer that determines their chemical properties, their propensity to associate or reassociate with other atoms when they are in close contact. But there is another type of bonding between atoms, when one atom gives one or several of its electrons to another. For example, let's say one atom has 1 electron on its second electronic shell that can hold up to 8, and another has 7. They could both benefit in terms of stability of the first atom giving its single outer shell electron to the second one, so that they will both have their outer shell complete. But when this happens, the two atoms become electrically charged. The first one now has one more proton than electron, and the second one has one additional electron. As we have seen before, they turn into ions, one negative with a negative charge, the other with a positive charge. Due to electromagnetism, they both turn into tiny magnets that are attracted to each other, so they stay stuck to each other. An example of this is sodium chloride, also known as table salt. Sodium and chloride tend to turn into ions when in contact. Sodium atoms lose an electron and chlorine atoms gain one. They automatically bond because their electric charges become opposite, and this forms table salt. This is a good example of how chemical bonding and the interactions between these tiny electrons can dramatically change the properties of matter. In atmospheric conditions, sodium alone can be dangerous because it is explosive. It spontaneously explodes in presence of water because it bonds with oxygen, and this releases hydrogen. Chlorine forms a gas in the atmosphere that is very toxic, but the two together create a compound that is perfectly stable and harmless. I told you before that even though molecules were very common in our biosphere, this form of grouping between atoms was far from systematic. Actually, most of the matter under our feet, from the crust to the core of the planet, is not made of identifiable molecules. There are other types of chemical bonds. For example, what happens with metals. It is interesting to spend a bit of time on metals, because this is another term that has different definitions, and they can be confusing. In everyday life, what we call metal is a material that is hard at normal temperature, that can be polished and will look a bit shiny, and it conducts electricity and heat rather well. That includes iron, copper, zinc, gold, silver, and also alloys like steel, which is an alloy of iron and carbon. This is a convenient definition, but not a scientific one, since it mixes up basic elements and compounds that are made of several different elements. And it is also based on room temperature and common conditions of pressure. Metals can also be liquid or gas if they are heated enough, so their hardness doesn't define them scientifically. So in physics or chemistry, metals are not exactly the same thing, even though there is an overlap in definitions. A metal is defined as a substance capable of conducting electricity at a temperature of absolute zero, the total absence of heat. Based on this definition, the metals I mentioned before, like iron or gold, also are metals in physics or chemistry terms. But elements can become metals under high pressure, even when they are not defined as such at room temperature. For example, iodine, which is a non-metal unless it is exposed to a pressure of 40,000 times atmospheric pressure. When it is, it becomes metallic. And equally, some materials that are metals at atmospheric pressure, like sodium that we mentioned before, become non-metals. In the case of sodium, it requires pressure of 2 million times atmospheric pressure. Of course, this cannot happen naturally around us, but inside the core of a planet, it can. So, metals conduct electricity well. But why is that? As we have seen before, electricity is a movement of particles, especially electrons. And metals are a favorable environment for this movement because they form objects with a lot of free-moving electrons that are not attached to specific atoms. They form what is called metallic bonding, which is a form of chemical bonding in which you have plenty of atoms that are positively charged. They lack electrons that would make them electrically neutral. And these atoms share free electrons that stabilize the structure. So if you take, let's say, a piece of iron, there are no individual molecules inside. It is one single block of atoms bound together by the sharing of their free electrons. The presence of free electrons, this metallic bonding, accounts for many properties of metals, like their strength, their electrical and thermal conductivity. That's why electric wires are made of metal, copper generally. The structure of a metal wire can be pictured as plenty of positively charged atoms, ions, held together by an ocean of negative electrons. This is metallic bonding. Now metals can also exhibit other types of chemical bonding. I told you earlier about sodium forming table salt with chlorine, or iron can bond with oxygen. This is what happens when rust appears. But once a metallic bond is formed, the atoms in metal tend to have a strong attractive force between them. Much energy is required to overcome it. And this is why many metals have high boiling points, generally several hundred degrees. So, as you see, there are different types of grouping between atoms, and the way they form bonds into much bigger objects with atoms of the same kind or different kinds is determined by their electrons. But let's go even smaller and look inside an atom. We are now on a scale that is beyond what a microscope can see. I told you before there are around 30,000 billion cells in a human body. Cells are made of billions of atoms. An estimate of the number of atoms in an average person is 7 followed by 27 zeros, or 7 billion billion billion. And even though there are dozens of different elements in a human body, only 3 of them, 3 types of atoms, add up to 99% of the total. Hydrogen, which is about 2/3 of the body. Oxygen, which is 1/4, and carbon for 1/10. A lot of this is water, hydrogen and oxygen. But these three atoms combine with others into many different types of substances that make the most part of our physical bodies. Atoms may be tiny, but they are empty space for the most part. Imagine an atom has the size of a stadium. Then the nucleus would not be bigger than a tennis ball at the center, and the electrons would appear to be very far from it. The space in between is empty. But this is an image because electrons are revolving very fast around it. They form like a cloud around the nucleus. So it may be more accurate to picture the atom as a dense nucleus and a cloud around it, a zone with lower density. What keeps atoms together is the electromagnetic force, this interaction we already talked about, one of the four fundamental interactions. Protons are positively charged, electrons are negatively charged. This is just a convention to describe opposite forces, of course, so they stick together. But except for hydrogen, which only has one proton, the nucleus has several protons. If we follow the logic of electric charge, these protons should repel themselves, and the nucleus should not be stable. But it is, because of another force, one that plays on very, very small distances, and is powerful enough to overcome the electromagnetic force. And this force is called the nuclear force. It binds protons and neutrons together, and it makes the nucleus very stable and hard to crack. This nuclear force was considered to be one of the four fundamental forces or interactions I mentioned before, the strong interaction. But since the 1970s, it appeared that it was not exactly like this. The nuclear force is a residual effect from a more fundamental force, one that keeps even smaller particles together inside protons and neutrons. And the nuclear force is a side effect, a residual effect of this more fundamental interaction. But it is what keeps the atom's nuclei together. However, all nuclei are not perfectly stable. A big nucleus may fission, which liberates a lot of energy, and this is the mechanism used in nuclear reactors. When they absorb additional nutrients, heavy and unstable atoms like uranium or plutonium become so unstable that they fission into smaller nuclei. Or even without fissioning, nuclei may be subject to something called radioactive decay. Due to their instability, they lose energy by radiation. The nuclei emit one or more particles or photons, a particular type of particle that has no mass. There are different types of radioactive decay. One of them, beta decay, is caused by the fourth fundamental interaction, called the weak force. Everything we have seen before, as we advanced from our scale to smaller and smaller levels, was relatively easy to picture because it obeys to forces and laws we are familiar with. Mass and gravitation, electric charge and electromagnetism are concepts we can understand and apply to a smaller scale in our head. But once we enter the realm of subatomic particles, it becomes much less familiar and close to impossible to picture, because maybe the most important discoveries in physics since the second half of the 20th century are about the exploration of a world where what we thought we knew about matter, based on our sensible experience and the state of science until then, no longer applied to the subatomic scale. In this realm, particles can exist without a mass, which is not easy to accept since we are conditioned to think that any real physical object has to be made of matter, made of something tangible. In this tiny world, particles become unpredictable, and you cannot know where they are. The distinction between energy and matter, or between a wave and a particle, they all get blurred. The tools to approach this reality are no longer in our sensible experience and logic, but rather in mathematics and hypotheses that defy our imagination. To approach the physical properties of nature on an atomic and subatomic scale, the best theory or field of investigation we have available at this point is called quantum mechanics or quantum physics. Quantum mechanics is not that recent. It arose gradually, starting a century ago, as a reaction to observations that could not be reconciled with classical physics. Until 1900, scientists had managed to describe many aspects of nature at an ordinary scale. One cornerstone of classical physics, and it remains very useful nowadays, was Newton's theory of gravitation. It worked for bodies on Earth. It seemed to work well for planets and stars too. So from there it was tempting to extrapolate to all scales and consider that the fundamental laws of physics were already understood. That was very much the consensus by the end of the 19th century. Scientists knew that a lot remained to be explored on a very small or on a very large scale, but the laws that governed matter were not a big concern. Until this comforting feeling began to crumble due to observations that did not correspond to what was expected. The works of scientists like Max Planck and even more Albert Einstein shook the world of physics, because they showed that the world was not exactly what it seemed to be. Things that were seen as constant, like the passing of time, were not. There may be more dimensions than the familiar 3 dimensions of space. Particles did not behave as expected. The distinction between a particle and a wave was blurred. A bit later, radioactivity was discovered, proving that matter and its interactions were much more complex than thought. Quantum physics was born on the need to explain or to refound physics on a very small scale, to explain how atoms and the particles they are made of work. It is a field, not a single theory. It is based on a mathematical framework that was developed in the 1920s by physicists like Werner Heisenberg or Niels Bohr. The basis of quantum physics, quantum mechanics, and this is where it is not intuitive at all because it contradicts classical physics, are first that certain properties like the position or the speed of something do not follow a smooth, continuous spectrum. Instead, properties click from one state, one position to another. Let's take an example with light and colors. For a long time, it was believed that light was just a wave. 200 years of experiments had showed that light behaved like one, until Max Planck analyzed in detail the distribution of colors emitted by a light bulb. Logically, if light was only a wave, the distribution of colors along the spectrum should be perfectly smooth, with the same gap between each specific color emitted. Planck realized that even though a great number of colors were emitted on the spectrum, there were holes on it. Only combinations of certain colors were emitted, instead of having colors evenly distributed on a continuous spectrum. This meant that something prevented atoms from producing the colors that should have occupied these gaps. The term that was later coined to describe this is quantized, which gave quantum properties, in that case color, but it applies to other properties like position or speed, can jump from one set amount to another. Decades later, this intuition was confirmed many times by experiments. Particles may or may not be where we would expect to find them. They may occupy a position, and in their next set of properties be somewhere else, without consuming time to travel from one point to the next. And yet, be somehow connected to other particles. This defies imagination, but a metaphor to try to picture it is imagine a dial. Properties click like a dial that changes settings. Another fundamental principle is that light can sometimes behave as a particle, one that has no mass, and matter, despite having a mass, can also behave as a wave. Within the field of quantum physics, different theories explain the fundamental forces by which matter interact that we have talked about before. Electromagnetism, that explains how atoms hold together. The strong nuclear force, that explains how the nucleus remains stable. Or the weak nuclear force, that explains why radioactive decay occurs to some atoms. At this point, the various theories that explain these forces have been regrouped under an umbrella called the Standard Model. This model explains 3 of the 4 fundamental interactions. The fourth one, that is out of the field at least for now, is gravitation, that appears on a macroscopic scale, not at the atomic level. The Standard Model describes a lot of different elementary particles. Matter particles, also known as fermions, like leptons and quarks, that come in 6 different types each, and force carriers, also known as bosons. One major challenge is to unify these theories that are connected by their principles but do not form a single theory of matter, and maybe one day reconcile them with gravitation, because they do not explain this force nor connect it to their description of the infinitely small. However, the Standard Model has been vindicated several times over the past 3 decades with the discovery of particles that had been predicted theoretically but never observed before. Their presence could be proven through experiments in particle accelerators. The one discovery that garnered a lot of attention in the media was the Higgs boson in 2012. It had been predicted in the 1960s as the particle that gives all other particles their mass, and the fact that it was tested 50 years later shows that quantum mechanics is a powerful field. It works, but quantum physics remains very hard to present to the public because it makes predictions, it anticipates things about matter that seem to be completely at odds with how things seem to work in the world we experience. It says that particles can either be located in a single place, or they can act like waves and be distributed all over space, or in several spaces at once. How particles appear to us depends on how we choose to measure them, which questions the nature of reality itself. Is it something independent from our perception, our measurement of it? Also puzzling is the fact that quantum particles seem to be able to affect each other even when they are far away. And we ignore how this is even possible. This seems so far from what we know of reality or how we experience it, that some think there may be a more intuitive theory one day that remains to be formulated that could better unify and explain these forces and these observations, like Einstein did when he explained gravitation with his second theory of relativity. Maybe like Einstein did with the concept of space-time and its curvature, there could be a concept that would embrace all these elementary particles and their interactions. This is certainly the holy grail of physics at this point. In another story, years ago, I told you about nuclear fission and how big atoms, like uranium or plutonium, could become unstable when they captured an additional particle, a neutron, which made them split into smaller atoms. This fission also liberated more free neutrons that escaped from the fissioned atom and could participate in other fission reactions, leading to a chain reaction. The fission of atoms liberates a lot of heat and a lot of very fast particles that are ejected from the fissioned nuclei. And this is the mechanism that produces energy in a nuclear reactor, in which this reaction is piloted to keep it working without snowballing. And the constant heat produced when the reactor is in operation is used to heat water that turns into steam and powers electricity generators, turbines. As a power source, nuclear fission has its advantages compared with fossil fuels or the various kinds of renewable energy sources. It is very compact relative to the power it can provide. A single reactor or a nuclear plant, which often has several reactors, can provide electricity to millions of homes. It also rejects no greenhouse gases, contrary to coal, oil or gas. And its production is fairly reliable over time. It can work day and night. It is not dependent on winds or the intensity of sunlight or the accumulation of water reserves behind a dam, like for hydropower. But its biggest flaw is the radioactive material it uses and the radioactive waste it produces. If there is an accident in a power plant working with gas, it can be bad, but it remains localized. Whereas a nuclear reactor with highly radioactive material in its core can be a big hazard if an accident happens and there is a breach of containment. And the problem doesn't end with the reactor. Once nuclear fuel has been used, it turns to waste, and these used nuclear materials have to be monitored for years. First in pools where they are kept underwater while they cool down, and then they have to be stored somewhere underground. Because part of this nuclear waste will remain dangerously radioactive for hundreds of thousands of years. Nuclear plants and spent fuel tanks are operated with a lot of precaution. There are security measures, there are containment systems, but still, disastrous accidents have happened in the past. You obviously know about Chernobyl and more recently Fukushima in Japan. And even without accidents, the production of very long-life radioactive waste that future generations will have to deal with is a hazard and also a moral dilemma. So basically, nuclear energy with no radioactivity and no waste would be fantastic. It would eliminate all the main problems raised by nuclear plants since they appeared in the 20th century. And this is the promise of nuclear fusion, and the reason why it has been a topic of interest for decades. It could theoretically be a source of energy that uses no unstable elements for fuel, creates no dangerous waste, and on top of this is even more powerful than nuclear fission, which could make it very cheap. It sounds very good, and it is an exciting prospect for humanity, but it is not that easy. And I'm going to explain you why, how this power source works, how it could be harvested, and why it is technically so difficult. So to begin with, what is nuclear fusion exactly? It is a reaction in which two or more atom nuclei are combined to form one single nucleus. In other terms, it is atoms merging. As you know, atoms are made of different particles. In their nucleus, there are neutrons and protons, the difference between the two being that protons are electrically charged and neutrons are not. We'll come back to that. Around this nucleus, there are one or several electrons, which have an opposite electric charge to protons. And typically, an atom has the same number of protons and electrons, which makes it electrically neutral unless electrons are missing. Even though atoms are made of smaller particles, they are considered a relevant unit of matter for mainly two reasons. First, because they define each element depending on how and how many of these particles combine. Protons, neutrons, and electrons, you get different elements with different properties. Atoms of hydrogen, iron, copper, gold, or carbon, they are all made of the same basic bricks, but it is how many and how they are combined that give them different properties. This makes the atomic level very relevant to physics, chemistry, to more generally the understanding of the properties of matter. The second reason that makes atoms relevant is that most of the time atoms around us on our planet or other planets of the solar system are very stable. They keep the same structure over very long periods of time because it takes extreme conditions to break or change the nucleus of an atom. With very little risk of error, I can safely tell you that almost all the atoms in your body have existed for billions of years. Maybe not combined together in the same molecules, but as atoms they already existed in the early stages of the formation of the solar system. Outside of stars like the Sun, and we're going to talk about that extensively in a minute, atoms generally don't change. The only exception on our planet would be a few big atoms that are naturally unstable and experience decay. They fission naturally because their nuclei formed with a number of neutrons that makes them prone to breaking apart. But this is a very small share of matter on Earth. Other than that, atoms exist for very, very long periods of time. But this raises a question. Why are there atoms? Why do the particles, the components of atoms, stick together and so firmly instead of flying past each other? It is important to understand it to grasp what happens in a fusion reaction. There are basically two forces that keep atoms together. The first one has to do with electric charge. I told you earlier that protons in the nucleus had a small electric charge, marked as positive, and electrons have a negative charge. This is what bounds the nucleus and its electrons. Opposite charges attract each other, and similar electric charges have the opposite effect, they repel. As a result of this, a nucleus which is positively charged will attract electrons that will swarm around it. This is the first force that keeps atoms together, the one that binds electrons to a nucleus. But this raises a common sense question. If electrons are attracted by the nucleus, why don't they just merge with it, collapse into it? We may ask this question because of how atoms are generally represented, since the 19th century. The typical picture of an atom is like a mini solar system with electrons orbiting around a nucleus, like planets orbit around a star, but on a very, very small scale. So, based on this representation that still dominated physics a century ago, the first hypothesis was that electrons kept separate from the nucleus because of centrifugal force. If they revolved very fast around the nucleus, then it made sense that they wouldn't fall into it, because this centrifugal force would maintain a distance. In that hypothesis, the orbit of the electron around the nucleus would have been the product of an equilibrium between the electric attraction, the force that pulls the electrons towards the nucleus, and the centrifugal force that pushed it away. This could work, but only if we accept the representation of an atom as a tiny star system. But what modern physics tells us is that this representation is not accurate. It appeared about a century ago, in the 1920s, that a tiny object such as an electron could not be treated as a classical particle with a definite position and a definite velocity. This is the realm of quantum physics on this scale, and we cannot always know where an electron is. We can only observe its manifestation sometimes. And it doesn't follow an orbit around the nucleus. It manifests itself near or even sometimes inside the nucleus. This is not our topic tonight, but just bear in mind that the traditional image of the electrons orbiting around the nucleus is something that modern physics no longer validates. It is still useful to picture an atom, understand its interactions, but a better image of what an atom is would be with a nucleus and a kind of cloud around it. A cloud that represents all the locations where electrons are likely to be at any given time if we observe them. This is hard to picture mentally, and this is probably why the old atom picture with electrons in orbit is still enduring. But that was just a tangent to explain why the idea of electrons falling into the nucleus because of electric charge's attraction doesn't really have a basis. It is more a false problem created by our traditional representation of atoms. And for the topic we discussed today, let's just bear in mind that the first force that holds atoms together is electric charge, that binds electrons to the protons contained into the nucleus. But at this point, you could tell me that we have a problem. If opposite electric charges attract and similar charges repel, then the nucleus should not exist, it should explode, because it contains protons that have the same positive charge. Why do these particles with a similar charge stick together? Obviously because there is a second force at play, one that is stronger at this scale and more than compensates for the electric force. All the more that the closer charged particles are, the stronger the electric repulsion is. This is why this force that keeps protons and neutrons together in the nucleus has been called the strong force or strong nuclear interaction. It has been identified in the 1970s. It is not that long ago as one of the fundamental forces of physics. What is a fundamental force or a fundamental interaction? They are existing forces that do not appear to be reducible to more basic interactions. We can observe them, measure them, anticipate their effects, but they cannot, in the current state of science, be explained by another interaction behind it. 4 of these fundamental forces have been identified until now, and we just talked about 2 of them. We talked about electromagnetism, which is at play in the attraction between protons and electrons that keeps electrons bound to atoms. We know this force is there. We can explain and measure how it works, but we cannot go much further and understand why, at least until now. It is the same for the second force we just talked about, the strong nuclear interaction that holds nuclei together. It also holds individual particles like protons and neutrons together, because they are made of even smaller particles. And we know a bit about the how. This force is carried by subatomic particles called gluons and mesons, but the question of the why, or if there is another interaction behind it, remains unanswered. The strong nuclear force works on a very small scale, a very small range, the scale of a nuclei or individual particles. But at this range, it is very, very powerful. At a range of about the radius of a proton or a neutron, it is more than 100 times stronger than electromagnetism, which is why it easily compensates for the mutual repulsion of protons due to their similar electric charges, and it holds the nucleus together firmly. There are 2 more fundamental interactions. Another that exists at a subatomic scale too has been called the weak nuclear force, or weak interaction. Its range is even shorter than the strong interaction. It acts inside particles, and it is the hardest to understand. We don't need to go too far in that direction tonight. But let's keep in mind that the weak force is an interaction that exists inside the components of atoms. It doesn't bind them together, but plays a role in their transformation. For example, a proton can become a neutron. It can lose its electric charge. The weak force is important in processes of decay inside atoms, which come with the emission of radiations. So it is a third force, and the 4th fundamental force, which manifests itself on a much larger scale, is gravitation. This is probably the one we are most familiar with. It does not only keep together star systems or planets, it is also what gives us weight, makes objects fall. Here again, theories have explored gravitation. They have helped measure and define it better. For example, Einstein's theory of relativity, which defined gravitation. I made a story about it long ago if you want to know more about this theory and its implications. But even though the theory of relativity shed a new light on gravitation, it explains the how it works, but it does not offer another more basic interaction that would be behind it. This is why gravitation is considered a fundamental force too. Now this list of 4, electromagnetism, strong interaction, weak interaction, and gravitation, is not necessarily closed. Maybe a fifth one will be added to the list one day. Some physicists think there could be yet another one, or the list could shrink. Maybe two or more of these fundamental forces could be the product of a same basic interaction that has not been understood yet. One of the goals of physics, the discipline, that is still out of reach today, is to try to unify them, to understand why they exist, possibly as different manifestations of a yet-to-discover interaction. It will certainly never solve the ultimate why. If we discover another more basic interaction behind them, we still won't have an explanation of the why this other force exists. This is the field of metaphysics, what is above or beyond physics. But it would be fascinating and possibly have applications to unify some or all of these fundamental forces in a theory one day, if this is possible. So, now that we have seen a little bit more of why atoms held together and what they were made of, let's return to fusion and try to answer this question. Why would the fusion of two nuclei liberate or consume energy? Because, after all, why combining two things together would release anything? We have seen that nucleus, that is to say protons and neutrons, were held together by the strong nuclear force. This is key to understand what happens when nuclei merge. We know it since Einstein's theories. In physics, matter, a mass, a quantity, and energy, that is to say, the property that must be transferred, applied to a body to perform work on it or to heat it, are not entirely separate things. They are manifestations of the same thing. It defies our conventional imagination and our sensible experience. But matter and energy are the same thing, hence the famous equation E, energy, is equal to m, mass, multiplied by the square of light speed. E equals mc squared. For more explanations about this, you can also listen to the story about the theory of relativity. But for tonight, let's just keep in mind that if the mass increases, then energy has been consumed, absorbed, and if a mass decreases, then energy has been liberated. What does it tell us about atom nuclei? That theoretically, if you take several particles that are independent, and then they form an atom nucleus that is bound by the strong nuclear force, then a form of energy that wasn't there before, when the particles were separated, has appeared, and it now binds them. The particles were not bound, and now they are. This work of binding them together is energy. But energy does not appear out of nowhere. So where was it before? It was in the mass, in the matter. And this leads to the following observation that sounds counterintuitive, but it has been verified long ago. When you put particles together to form a nucleus, the mass of this nucleus is less than the sum of the masses of the particles, because a little bit of their mass has been changed to energy. This energy is called nuclear binding energy, and it is one of the applications of the E equals mc squared equation. If you know the measure of this energy, you can use the equation to calculate how much mass has disappeared, and vice versa. Knowing how much mass has disappeared, you can calculate the energy liberated. It also means that to disassemble a nucleus into separate protons and neutrons, one needs to apply to it at least as much energy as the nuclear binding energy, the one that keeps it together. The loss of mass when the nucleus formed represents the energy that was released at the time of the formation. This connection, this equivalence between mass and energy, is the reason why energy may be released, or sometimes consumed, we'll see that later, when atom nuclei change size and composition. This is why fission in a nuclear reactor releases energy. When a heavy nucleus fissions into two lighter ones, less binding energy is required, and so the difference is liberated as heat and radiations. More specifically, in the case of a fission reaction, this excess energy is emitted as gamma rays, an electromagnetic radiation, and also as kinetic energy, that is to say, the movement, the velocity of particles that are ejected from the nucleus. In fusion, when nuclei merge instead of fissioning, there is also a variation of the quantity of binding energy required. If it is less, then the difference is liberated, released, or sometimes it can be more. Fusion may also require more binding energy for the new nucleus to hold together, in which case the fusion reaction has a negative energy balance. One has to give energy to the particles, and in that case, the reaction is called endothermic, whereas when it liberates energy, it is called exothermic. Now, if we want to harvest energy from nuclear fusion, we need to combine nuclei that will need less energy when put together into a heavier nucleus, a heavier element. But what makes the difference between fusion reactions that liberate energy and the ones that consume some? The size and the structure of the nuclei are key. Typically, the fusion of light, small nuclei, elements that are the first ones in the periodic table of elements, like hydrogen or helium, liberates a lot of free energy. The most common type of fusion reaction in a star, like the Sun, is the fusion of hydrogen nuclei. The most abundant type of hydrogen atoms in the universe, more than 99% of hydrogen, only has one proton and no neutron. So basically, an isolated proton is a hydrogen nucleus. When hydrogen atoms only have one proton as a nucleus, they are called protium. But as you know, there are variants of atoms. Sometimes they can have additional neutrons in their nucleus. These variants are called isotopes. And hydrogen has one which is less common than protium, but still fairly abundant in the universe, called deuterium. Its nucleus contains one proton and one neutron. There is another isotope called tritium, which is one proton and two neutrons as a nucleus. So, when you put together two such nuclei, let's take, for example, two isolated protons, the most simple kind of nuclei. You get a more massive nucleus, but as we have seen, not as massive as the sum of the two protons, because a part of their mass has turned to energy. In practice, inside a star where this reaction takes place, neutrons are added to the mix. It is not just two protons, and the fusion of two hydrogen nuclei can give a variety of isotopes of helium, the element just after hydrogen in the table of elements, because it has two protons in its nucleus. Helium with two protons and zero neutron is very unstable and will quickly break apart. But helium-3 or helium-4, that is to say with 3 or 4 particles in the nucleus, 2 protons plus 1 or 2 neutrons, these are very stable. The constant fusion reactions that happen in a star are what powers it, because they liberate enormous amounts of energy, radiations, heat, particles with kinetic energy. During most of its lifetime, a star lives on the fusion of light atoms, essentially hydrogen, and then helium to a lesser extent, and it creates heavier nuclei, but not the heaviest elements, because, as we just said before, these ones require an absorption of energy. Their creation costs energy instead of releasing some. The limit in the list of elements where fusion begins to need an input of energy is an isotope of iron called iron 56. It has 56 particles, protons and neutrons, in its nucleus. The creation of elements that are heavier than that via a fusion reaction is endothermic. It consumes energy instead of releasing some. And for that reason, it is believed that the appearance of these heavier elements takes place in the last phases of a star's life, when it has exhausted a large part of its hydrogen available and ends in an explosion, a supernova, followed by a collapse. The energy released in a fraction of a second at that moment is so gigantic that heavy nuclei fusion, absorbing some of this energy. But what is important to understand here is that to harvest energy from a fusion reaction, you need to make protons come close enough from each other that the strong nuclear force, that is very powerful but has a very short range, can come into play and overcome the repulsion between the protons that is due to their electric charges. Before they are close enough, they repel each other, and this natural repulsion needs to be overcome by giving them enough energy so they can beat the electromagnetic force. In other words, to harvest energy from fusion, you need to spend energy first. And then, when fusion happens, you will get back more than what you spent. But there cannot be fusion without an already intensely energetic environment. This is why it happens in stars, where heat and pressure conditions are extreme due to gravitational forces. A star is a very large and massive body. The forces inside defy imagination. But in space, in the void, on planets, fusion cannot naturally occur. This is a big difference with fission energy. Fission happens because of the natural instability of nuclei. It occurs naturally on Earth. which is why there is a low-level natural radioactivity around us all the time. In a nuclear reactor, we just put a lot of fission-prone, of fissile material together, and then we start and pilot a reaction. But we don't need to give it energy for the fission reaction to begin. Fusion is much harder to ignite. It is theoretically conceivable to make it self-sustained. Once fusion reactions begin inside a contained space, they can liberate energy that will allow more reactions to happen. But the ignition costs energy. A challenge to turn fusion into a power source is to create an environment inside a reactor where fusion happens continuously, and the energy it liberates allows more fusion reactions to take place, so that the balance of energy is positive. And this is the technical challenge we are now going to discuss. How to create a confined reactor inside which temperatures are somewhat similar to the inside of a star. In reality, even higher, because inside of a star there is a very high pressure due to gravitation that cannot exist inside a reactor. So the temperature needs to be pushed even higher. We are talking more than 100 million degrees. That is to say, a temperature that can quickly melt any material we know of. But this incredibly high heat needs to be confined inside the reactor, and on top of that, we need ways of extracting the energy liberated by fusion. This is the extraordinarily complex engineering challenge raised by fusion power. Inside a star, a long-lasting fusion reaction can exist because gravitation provides confinement. The star is held together by gravitation. It is very large, so reactions can take place inside, and yet the star does not explode or dissipate in space because gravitation pulls all its components towards the center. For artificial fusion to be viable, we would need to recreate these conditions. But obviously gravitation cannot provide confinement because it would be on a much smaller scale. In a nuclear reactor, this problem does not exist because there is no requirement of high temperatures and pressure for fission to happen. So a tank filled with water and rods of fissile material, of fuel, is sufficient, and provided the heat from the reaction is evacuated constantly, this is how we harvest calorific energy in such a reactor. The tank will not melt because the temperature of the water inside does not go above a few hundred degrees. The temperature necessary inside a fusion reactor is completely on another scale. Punctually, where the fusion reactions take place, it is more than 100 million degrees. And even if this doesn't touch the walls of the reactor, these walls would have to bear extremely high temperatures. The constraints are challenging, to say the least. And this is why, from the moment artificial fusion as a source of power began to be researched in the 1950s, the idea of confining the reaction inside a magnetic field appeared. But what does it mean exactly? First, we need to talk about what needs to be confined. What happens to matter when it is exposed to extremely high temperature? Matter in such an environment turns into plasma. But what is plasma? Generally, we learn in school that matter has three fundamental states: solid, liquid, or gas. The understanding of this in the 18th and 19th centuries was an advance in modern physics and chemistry, and these categories remain useful because indeed this is how we encounter matter on Earth in our daily lives. Assuming we are at sea level pressure on Earth, if you take a solid and heat it, it will turn to liquid, and if you heat it more, it will become gas. But these three states do not really grasp the entire spectrum of states of matter. For example, recently I told you about supercritical fluids in a story about astronomy. The atmosphere near the surface of Venus, or the layers inside gas giants like Jupiter, would be in that state that is neither liquid nor gas. There is another state called plasma, and even though we naturally encounter it rarely on Earth, it is actually by far the most abundant state of matter in the solar system, and also probably in the universe, because this is the state of most of the matter inside the stars. And the Sun, just to take our system as an example, accounts for more than 99% of all matter in the solar system. Plasma is what you get when you superheat a gas, so hot that the electrons are ripped away from the atoms, forming what is called an ionized gas. Ionized because ions are particles, atoms, with a positive electric charge. A proton alone, or an atom that misses an electron, are ions. Taken as a whole, a plasma does not necessarily have a positive or negative electric charge, because the charges of its particles compensate each other, as long as it contains as many electrons as ions. But the plasma acquires different properties, and the most important is that it becomes electrically conductive. It reacts to magnetic fields, because this cloud, this soup of particles, will move collectively due to its electric conductivity. Now, the concept of plasma in everyday language is a bit blurred, because there is no exact definition of the transition point between gas and plasma. There are things like neon lighting or plasma screens. These have more or less disappeared now. They have been replaced with other technologies like LCDs. But these are applications that use plasma, and obviously a neon bulb or a plasma television did not warm up to thousands of degrees. This is because they contain gas that is only partially ionized. It is not pure plasma, but it still has specific properties that can be used when you power them with electricity. Ionization is a spectrum. It can be only a few particles or all of them. The plasma we are talking about in a star or inside a fusion reactor is fully ionized. It is so energetic that atoms have been stripped of all their electrons, leaving only bare nuclei. This is what is needed for fusion inside a plasma to happen. A soup or a hot cloud of nuclei and free electrons, inside which nuclei that are now positively charged electrically are energetic enough, very hot, very fast, that they can collide despite their electric repulsion. They have the same electric charge, you remember. they can come close enough for the strong nuclear force to overcome their electromagnetic repulsion, and they can fusion into heavier nuclei. The elements, the fuel that can be used, are very important here, because as we have seen before, only fusion of small nuclei releases energy. They are called exothermic, as opposed to endothermic when they consume some. So the best fuel possible is hydrogen, because first it is the lightest possible nucleus, and second it only has one electron, so it is easier, it requires less temperature, less energy to ionize it, to rip the single electron off from each atom and turn it into an ion. The confinement of a plasma that is heated at more than 100 million degrees is inconceivable with walls. They would melt immediately. But as we have seen before, plasmas are electrically conductive, and so they can be controlled with magnetic fields. Possible designs of fusion reactors take advantage of this to confine the particles as they are heated. The plasma cannot touch the walls of the reactor, but what if we control the plasma inside, in suspension, with magnetic fields, so that it doesn't touch the walls? This idea, which is also a necessity, is the basis for all the designs of fusion reactors, including the most famous of them called the Tokamak. Tokamak is an acronym in Russian, and it has passed to other languages, but the name comes from Russian because this type of device was conceptualized in the 1950s by Soviet physicists. For the record, one of them was Andrei Sakharov, who later became very famous for being a dissident to the Soviet regime and a human rights activist. So the tokamak is only one of several types of magnetic confinement devices that were and continue to be developed to produce fusion power. If one day we manage to have a functioning fusion reactor, that is to say with a positive energy output, it will not necessarily be a tokamak, but it is one of the best, if not the best candidate. The inside of a tokamak looks like a ring, and it is made to contain plasma in the shape of a torus, which is the complicated word to say in the shape of a donut, a thick disk with a hole in the middle. Why a donut? Because it is an optimal shape, having magnetic lines that wind around the torus strongly helps to stabilize, to keep in place the plasma. Other types of designs have been imagined before or after. They are called stellarator, Z-pinch or magnetic mirror. We won't go further tonight into these types of devices. There are different approaches to plasma confinement with magnetic fields. They all have or had, when they were abandoned, their advantages and disadvantages. The biggest disadvantage for such a system is the loss of plasma. If it doesn't stay in suspension, but leaks, escapes from the zone where it should be confined. You understand the complexity of this. It is necessary to make plasma that will be several million degrees hot stay in suspension, levitating, inside a reactor, while at the same time particles inside the plasma move at speeds that defy imagination. When it was invented in the 1950s, the tokamak design was a leap forward. because it suppressed the instabilities that plagued earlier designs. At the end of the 1960s, Tokamaks looked very promising. They had not achieved a net positive output of energy, but they had better results than any other designs, and that's why they multiplied around the world in research facilities. But then, bigger and bigger devices, made with the hope of reaching a positive output, disappointed. They encountered new problems when they were built on a larger scale, and there were disappointments in the 1980s. The reason why the output remains negative is not that these reactors don't achieve fusion, they do. They heat plasma in suspension. This is complicated technically, but doable by inducing a powerful electric current inside the plasma. You remember, the plasma is conductive. Then fusion reactions begin, and new fuel, new hydrogen has to be introduced to keep the reactions happening. But the problem is that the heat generated by the reactions is not sufficient to make more reactions happen and make the reactor self-sustainable, while at the same time harvesting some energy from it. The plasma cools down when heavier elements, the products of fusion, accumulate in it. The plasma is not stable enough, it leaks, so more power has to be given to the reactor to make it continue to work. And instead of producing a net surplus of energy, the reactor needs an input. As of today, the machine that holds the record for fusion output is the JET, J-E-T, the Joint European Torus, which is located in England. Its output reached 16 megawatts, but for an input of 24 megawatts, so it is still significantly negative. But still, progress has been made in the past decades. These performances are well above the ones that were achieved with the very first devices, and hopefully they will keep improving with better materials, better fuel, bigger devices too. Research continues around the world, and because it requires extremely complex engineering, expensive equipment, large teams of scientists and technicians, some of these efforts are international. The primary international effort to advance towards a practical fusion reactor today, and it is based on a perfected tokamak design, is ITER, I-T-E-R, the International Thermonuclear Experimental Reactor, a project that is still under construction in southern France, and when it opens in a few years, it should be the largest tokamak in the world, and more generally the largest experiment for containment of plasma, with 10 times the volume of any other tokamak operating today. Parts of the hopes placed in this project rely on the change of scale, to be able to generate a net positive output. If this works, how could such a reactor harvest energy? The energy liberated by exothermic fusion comes under the form of heat and particles that have kinetic energy. They are expelled from the new nucleus, and when these particles are neutrons, they are not bound by the magnetic fields that keep the plasma in place. They have no electric charge, so they are not affected by the magnetic field. So they are going to escape the plasma and hit the walls of the reactor, which will heat them up. Through this mechanism, calorific energy, heat, can be extracted. Like in a fission reactor, it can be extracted by a fluid, water, in circulation that comes in contact with the hot walls and be used as steam to power turbines that produce electricity. If this can be achieved, the reactor would have several advantages over other energy sources. There would be no release of pollutants, like with fossil fuels, and the main products of hydrogen fusion are helium atoms, which are not radioactive nor dangerous. There would be only a marginal creation of radioactive waste, still a little bit, not because of the fusion reaction itself, but because of the absorption of neutrons by the surrounding material inside the reactor. But not a big deal as far as we know today, because these byproducts would have a short half-life. They would quickly lose their radioactivity, and they are way less toxic and dangerous than the waste products of a nuclear reactor. It is almost sure that we will not see a functional fusion reactor this decade, and probably not in the next neither. So there is very little hope that they can solve energy issues in the short term. But however complex the engineering and difficult the task, the potential rewards justify the effort to design one. The fuel would be cheap, hydrogen is abundant. The one that should be used in such a reactor would have to be processed, because it would work with hydrogen that has one neutron. We talked about it before, the one called deuterium, and tritium, the one with two neutrons. Both, especially tritium, don't occur much naturally, so they would have to be produced, but that would still be cheap. The cost of electricity produced by fusion would essentially be the amortization of the reactors. They would be very costly at first, and the cost of maintaining and operating them. But just the environmental promise of very low waste and no greenhouse gases is attractive. So, where are we heading to find the center of the universe? Our ancestors believed that it was Earth, or the Sun, or much later the center of our galaxy. But we know today that these hypotheses don't really work in a scientific way. The first answer to this question, if we follow the Big Bang theory, is that we don't need to travel anywhere to reach the center. It's here. Not because Earth is at the center of everything, but because any point is as good as any other. There is no center to the universe we live in. What does it mean? You probably know the concept of the Big Bang theory. At some point in the past, billions of years ago, the entire universe was concentrated in a single point, and suddenly, like an explosion, this point expanded at speeds and levels of energy that defy imagination. This is not a bad metaphor, but it leads to a common misconception about the Big Bang that pictures it as an explosion in the void, as if the void of space pre-existed the Big Bang. If that was the case, the universe would have a center. In an explosion, the central point is the hottest point, from which matter and heat are projected in every direction. But this is not what the Big Bang theory says. The explosion did not take place in space. It was an explosion of space. What we call the void of space is part of the universe and enclosed into it. It is not something external. So rather than an explosion, an analogy that works better here would be one with a balloon that is being inflated. It expands in every direction. But imagine that the universe is not the ball formed by the balloon. It is its surface. Just the surface. Now, if we consider this spherical surface and ask ourselves where is the center, we could say that it can be any point. All points can be the center because relative to them, all other points are moving away as the balloon inflates. Or, put simply, if I give you a football or a basketball, you cannot point to one particular point on this surface that would be its center. We will talk in more details about the Big Bang theory, what it says and how it became the prevailing model describing the appearance and expansion of the universe. But before that, there is also a wealth of historical representations and other more modern theories to talk about. So let's take things from the start. Until the 20th century, the questions of the age of the universe, its size, or its limits were not that much studied by scientists. This question was more considered to be in the field of metaphysics, literally what is above physics, and cannot be grasped or described with scientific laws. A lot of different traditions and religions around the world provided answers about how the world had been created and when, or more exactly the Earth, whether it was seen as a world among others, a ball or a disk. What the ancient called the world was Earth, and the idea that the sun and the stars revolved around it was not really questioned. But this physical horizon started to be put into question with the progress of astronomical observations and the realization that Earth was an object in space, among others, that could actually be way bigger. Over time, new models put the sun at the center of the universe, like that of Copernicus in the 16th century, and they made Earth a planet among others in the solar system. Then the existence of our galaxy was progressively revealed, and in the 19th century, the Milky Way was often believed to be the universe itself, until it appeared that our galaxy was just one among others. So over several centuries, the size of the universe as we perceive it has increased dramatically, and our place in it as human beings living on planet Earth has been reconsidered in a way that is quite humbling. But another assumption in the 19th century was that the void in which the galaxy was floating, was limitless and ageless. It was eternal. This was not a theory or something people argued much about, just a hypothesis that answered questions about the frontiers of the universe. In a sense, this assumption was comfortable, because if the universe was eternal, then there were no questions to ask about its formation, its history, or its age. And if it was limitless, then this eliminated the question of what could be beyond its limits. But this had not always been the case. So how did men picture the cosmos, the universe, and our place in it along history? In many different ways. All civilizations forged their myth of creation, in which different gods were the artisans, or sometimes the products themselves, of the world's creation. I told you about some of these myths in recent stories about Greek, Norse, or Egyptian mythology. But maybe the Greeks were a bit different in their approach, because they introduced something else. The idea that natural phenomena were not just things to be observed or attributed automatically to the gods, but also things that could be understood and used for a better comprehension of the world. The Greeks didn't define the scientific method as we define the concept today, but they certainly elaborated its premises. Other cultures around the world also had an elaborate knowledge of astronomy, for example, like in Mesoamerica or in China. But they didn't go in the direction of observing the planets, the sun and the stars as physical objects that could be measured and speculated upon to better understand the harmony of the world as a whole. Doesn't mean the Greeks figured out everything, far from that. To them the world had to be geocentric, that is to say with Earth at the center and all other objects in the sky moving around it. This was a rather obvious observation to our ancestors. They saw celestial bodies move above their heads and come back year after year to the same positions. They had no reason to imagine that Earth itself was just one of them. And so the Greek world adopted the concept of Earth at the center of an universe, with celestial objects placed on another larger sphere that rotated around our world. This is how Plato, the philosopher, described the universe in the 4th century BC. The Greeks had found through deduction that the world was round, even though this was not intuitive or visible. This shows the power of their deductive approach to nature. They were ready to adopt a vision that was not immediately obvious to their senses, because it was logical. And the same logic made them question this description of the universe with a single celestial sphere carrying the planets and the stars around our world. They observed that something didn't work with the motion of the planets. They sometimes appeared to move backwards in the opposite direction to the stars and the constellations the stars formed. We know why today. Earth is in motion too in the solar system, so above our head other planets of the solar system can seem to go backwards on their orbit, not because they do, but because our vantage point is also moving, which can create this observation. In astronomy, this is called retrograde motion, the apparent change in the movement of a planet through the sky because of its relative position to Earth and how both planets are moving around the Sun at the same time. There was no way that all celestial bodies could be attached to this single external sphere then, and they came up with another explanation, also based on observation and deduction. Since the stars and the planets were not synchronized, it had to mean that there were not one, but several celestial spheres carrying objects in the sky. Up to 33 different spheres of larger and larger diameter rotating around us. Interestingly, the axiom that we were the center of the universe was not much questioned. It was taken as such an obvious thing that most of the Greeks didn't think about the possibility that Earth itself was moving. Most of the Greeks, because there were exceptions. For example, Aristarchus of Samos, an astronomer from the 3rd century BC, who had a remarkable intuition. He placed the Sun at the center of the universe and made Earth a planet among others. But his vision didn't stick and was mostly ignored, even though it was in a way more pertinent scientifically than the geocentric universe and its spheres turning around Earth. But however flawed this concept of multiple celestial spheres rotating around our planet was, there were also interesting and promising ideas in this depiction of the world. By considering that every planet was carried by a different sphere, the concept of orbits in space appeared. And overall, this depiction of the motion of the planets, the stars, the Sun, and the Moon above our heads was quite satisfactory at the time. So in the West, it remained the dominant scholarly description of the universe, not just for the period of ancient Greece, but for many more centuries, almost 2000 years, until the end of the Middle Ages. More significance and elements were added over time to this multi-spherical system to give it more spiritual meaning and connect it with natural sciences. Aristotle, for example, divided the universe into two parts. Everything up to the sphere that carried the Moon belonged to the changing and imperfect world where life, decay and death existed. This world, our world, was made of the four elements, water, air, fire and earth. Beyond the lunar sphere was the world of the high spheres, with the planets, the Sun and the stars, where everything was perfect and eternal. The Christian tradition also added elements to this worldview, especially a friar of the 13th century called Thomas Aquinas. He added yet another sphere beyond the last one where God would have resided, and from where he could embrace the entire creation. Angels lived in the solar and planetary spheres. The degree of divinity decreased as one moved down, closer to Earth. The purgatory, a notion that had been introduced in the Christian tradition during the Middle Ages, and also our world were part of the sublunar sphere. You see that there is still the influence of Aristotle in this worldview. And below our feet, even lower, underground, was where he placed hell, the land of evil, where bad souls ended after their terrestrial life. Men were placed in between the heavens, the high spheres of the divinity, and hell underground. Almost 2000 years with a stable description of the universe, and one that had been embraced and completed by theologians for centuries. This carried a lot of weight, and it is important to understand the reluctance to reject it, not from just the Catholic Church, but also many scholars of the 16th century, when new theories were put forward. Because these new descriptions of the universe could not just be scientific speculation. They shook centuries of tradition and the credibility of all these generations that had embraced this Greek and then Roman and then Christian system. The first and probably the most important intellectual revolution of the modern era when it comes to the description of the cosmos happened in 1543, when a Polish mathematician and astronomer called Nicolaus Copernicus published his description of the cosmos as a new system that put the Sun at the center of the universe instead of Earth. And he explained the movement of multiple planets around the Sun in a way that was very convincing, embarrassingly so, for the community of astronomers who knew about the movement of planets. The fact of replacing Earth with the Sun had big consequences, intellectual, cultural, emotional, spiritual even, because it also meant that humans were no longer at the center of the universe, and maybe not even at the center of creation. This heliocentric hypothesis, with the Sun in the middle, was actually not entirely new. As we have seen before, it was formulated in ancient Greece. But at the time it hadn't been successful enough to make a cultural or conceptual impact. In Copernicus' system, the theory of spheres was not rejected, neither. He just supposed that Earth was on one of these spheres, and the universe was much larger than thought before, because to him, the last sphere, the one that carried the stars, stood still, it didn't move, and it was the motion of Earth that now explained the apparent movement of the stars in the sky. But to make it work, to make it fit with observation, he had to place the last sphere much farther than thought before, beyond the limits of the solar system. So at once, humans were ejected from the center of the universe, and the universe became much larger than ever imagined. That was controversial, but it took decades until the early 17th century for the various churches, Catholic and Protestant alike, to attack these new astronomical theories, especially at the time of Galileo, another well-known and major astronomer. But attacks were not just on theological or spiritual grounds. Scientifically, Copernicus' system seemed to work well, but it had a few holes. One that served as a starting point to a Danish astronomer, Tycho Brahe, was the observation of comets and supernova. he saw in 1572, we are 29 years after the publication of Copernicus' system, he saw what looked like a new star in the sky, so shiny that it remained visible for a month, including during the day. He couldn't know it, but this was certainly a supernova in the constellation of Cassiopeias, the death of a dying star that liberated the energy of billions of suns in a few days. And this happened millions of years before the observation, the time for the light to reach Earth. But to him, if a new star could appear and disappear like this, it meant that the sphere of stars was not as immutable and perfect than thought since Aristotle, and even in Copernicus' theory. The sphere of stars could change. Another thing that caught his attention in 1577, 5 years later, was the appearance of a great comet, visible from Earth, and its trajectory could be observed. The trajectory formed an ellipse that seemed to cross several spheres, and these spheres were seen as material. They had to be solid to carry the various celestial bodies like the planets, otherwise the planets would have fallen. At the time, the concept of gravitation and the idea that bodies could float in space was not yet a thing. But if the spheres were solid, then how could a comet cross several spheres on its trajectory? Something was off. And even more in the early 17th century, when new instruments to observe the sky revealed that not only the moon seemed to have a geography, but other planets had satellites. This was when Galileo observed for the first time the 4 main satellites of Jupiter. In about 70 years since the publication of Copernicus' work, the old representation of the universe had crumbled, and new theories were popping up to explain the new observations made. On this path, the works of Galileo, then Kepler, Newton, very importantly for gravitation, that finally resolved the problem of these spheres that could definitely not be material. All of this made modern astronomy emerge, a science that was now primarily based on ever more precise observation. And when it comes to the field of cosmology, it had huge implications. Cosmology, the studies of the description, the origin and evolution of the universe, became a branch of astronomy or astrophysics. As a science, it was separated from tradition, religion, or myth. And it took decades, but this is another consequence of the intellectual revolution initiated by Copernicus' work. But due to its subject, cosmology also has connections to other disciplines, to philosophy, to other branches of physics, like particle physics. And as we are going to see, the Big Bang theory is an attempt at bringing together astronomy, the observation and study of the various bodies in space, and particle physics. So after this little historical overview, we are now back to modern times and the march to the formulation of the dominant theory that describes the history of the cosmos. I told you that new instruments of observation, new telescopes, had appeared at the time of Galileo in the early 17th century and allowed these observations. Technical progress didn't stop to our days, and in the 18th and 19th centuries, ever more bodies were identified in space, farther and farther from us, which also invalidated the heliocentric model. I already told you about the discovery of galaxies and how in our perception the universe became bigger and bigger along the past 2 centuries. That was in the story about galaxies. The link will be in the description. So I'm not going to repeat all this. But what interests us here is how theories about the cosmos evolved with these discoveries. As I told you at the beginning, by the end of the 19th century, the old theory of spheres was long gone, and even though this was not proven, a common assumption now across the scientific community was that the universe was limitless and eternal. It had always been there, would always be, and it was also static. In the first decades of the 20th century, it began to be understood that these distant nebulas that were supposed to be maybe island universes or clouds of gas were in fact other galaxies like ours. The central figure to the discovery of the multiplicity of galaxies was Hubble, the American astronomer. And something odd was noticed. These galaxies, especially the most far away from ours, seemed to be receding in space. They moved away from us. This was impossible in a static universe. And so a hypothesis was formulated in 1927 by a Belgian physicist, Georges Lemaitre. If objects were receding in space in every direction from our vantage point, it had to mean that the universe was expanding. In 1931, he went even further and suggested that if this expansion was projected back in time, then the further in the past, the smaller the universe was. And there even had to be a time in the past when all the mass of the universe was concentrated into a tiny single point. In the 1930s, Einstein's theories about time, space, energy and matter were already very well known, and the concept that they were linked was admitted. Here again, link in the description about Einstein's theory of relativity. So it meant that there had been a time when, suddenly, the fabric of time and space came into existence, when this tiny universe began to expand. This contradicted the steady-state universe conception that was preferred at the time, and initially the idea that the universe could have a history was rejected by many. Arguments against it included the fact that receding objects could have other explanations, so that was an unnecessary hypothesis. I'll tell you more on these alternative theories later. And also that the beginning of time was re-injecting metaphysics or religious concepts into cosmology. Georges Lemaitre was also a Catholic priest, which probably enhanced the perception that the Big Bang theory was an attempt at bringing together modern astronomy and the Christian belief in the divine creation of the universe. So in the 1930s and after, other theories that are now called non-standard because they have been rejected by the vast majority of experts and cannot pass peer reviews, were formulated. But in cosmology, non-standard doesn't mean necessarily false. A standard theory is a widely accepted one because it is backed theoretically and empirically by observations that fit with the model's predictions. New theories are non-standard until they are validated, but sometimes invalidated old theories do not disappear entirely. They keep a small core of supporters despite contradictory observations or flaws that made the scientific community reject them. When Copernicus published his main heliocentric theory, it could have been called non-standard in the sense that it went against the consensus. Then it became standard, but it didn't make it true either. No one puts the sun at the center of the universe anymore, and you remember that Copernicus didn't reject the theory of spheres, which was abandoned later. Einstein's theories also were non-standard when they appeared. So this whole movement with theories that emerge as an explanation, a new angle, should be seen as parts of a process. Now scientists and the general public also are human beings. The creators of a theory can be emotionally attached to it. There can also be appeal in holding non-consensual positions and getting a form of reward from it, from a sense of self-worth to the opportunity to join a community. So theories do not always die entirely, even when the scientific community as a whole moves away from them and ignores them because they are not backed by evidence or have been invalidated by new observations. Theories have to compete and prove their worth for their place in the sun. The theory of an initial Big Bang, when and where everything was concentrated in a single point, a singularity, began to gain more supporters in the 1930s and 40s. But the scientific community remained very split. On the other side were supporters of a steady-state universe. A new steady-state universe was formulated to explain how the universe can be steady despite objects receding. In other words, to explain how the density of the universe can remain the same when galaxies are farther and farther apart. This theory posited that new matter was generated, that there was a matter creation field that inserted matter into the universe to maintain a constant density. Why not? It is certainly not harder to imagine than the concentration of the entire universe into a single point. For 15 years, the two theories coexisted, but the Big Bang theory won thanks to the observation that its predictions worked. In particular, the concentration of the entire universe at the start would have implied that at the early stages of the universe, when the atoms began to form, there was a transition phase that should have left a trace, a cosmic microwave background, like a kind of white noise that would exist everywhere in the universe. It is not noise, of course, it is a faint radiation. This remnant or relic radiation was detected and measured in 1965, and it was a major game changer for the Big Bang theory, because it corresponded to its predictions, and this microwave background had no other known explanation. From this moment on, the alternative theories were progressively abandoned, and the Big Bang became the dominant, the standard approach to the description of the universe's history and its expansion. It fits with observations, it made accurate predictions, but it doesn't mean that the theory explains everything when it comes to matter in the universe. In the current state of cosmology, there is no theory of everything that would explain every single observation. Here again, there is more about this you can listen to with topics like dark matter in the story about galaxies. There are still alternative models to the Big Bang theory, or complementary models being worked on, that are based on new hypotheses for a steady-state universe. For example, one that supposes that the universe could go through successive phases of contraction and expansion, and we would be in an expansion phase, explaining Hubble's observation of the galaxies receding. But these are no longer mainstream, and the Big Bang is the standard theory since the 1960s and 70s. Many attempts at imagining and describing a different cosmology have been made in the past 100 years. More than a dozen looked serious enough to deserve conversation. The holy grail for a cosmological theory is to explain all observations made. That includes faraway galaxies receding, the laws of physics that seem to work well, like the existence of gravitation and relativity, the different forces that are observed with matter, from very small scales to very large ones. Hypotheses have been made to explain or challenge observations. One such hypothesis, for example, is called the tired light. What does it mean? I told you earlier that one major observation that participated in the understanding that the universe was most probably expanding was Hubble's observation that galaxies are moving away from the Earth at speeds proportional to their distance. The farther they are, the faster they move away. You remember the image with the inflating balloon at the beginning. If we are a point on the surface of this balloon and it is being inflated, other points on the surface will move away from us in every direction, and the farther they are, the faster they move away. But it is not that simple when it comes to measuring the velocity of galaxies that are millions of light years away from us. How do you know how fast they travel when they are just tiny points that are invisible to the eye and can only be detected by telescopes? Hubble's solution to measure their velocity was their redshift. The redshift is an increase in the wavelength of light that we receive from them. It is called redshift because of the color red, which is at one extreme of the visible light spectrum for us. The concept is that a galaxy is moving away from us and sending us light in the other direction. The movement of the galaxy relative to us alters the wavelength of light, and this is how we can measure its velocity from where we are. But redshift works as a measuring tool of their velocity only if the change in wavelengths comes from this growing distance between the galaxy and us. And this is where the tired light hypothesis was made. What if the distance was not changing in fact, but light was losing a little bit of its energy when it travels a very long distance. That could explain the slight increase in the wavelength, the decrease in the frequency. Tired light was abandoned as an hypothesis because it didn't seem to work for several reasons. No loss of energy for light was ever observed or explained, and also, if this theory was right, more distant galaxies would indeed be redder, but their surface brightness seen from Earth would also be stable, and it has been observed that the brightness evolved over time, which is not consistent with tired light, and actually backs the expansion of the universe theory. And then cosmic microwave background was detected, a huge argument in favor of the Big Bang theory, which sent the possibility of tired light into retirement. But as a question, it was a good intuition that deserved to be examined. An example of alternative cosmology that appeared in the 1960s and is now rejected by the scientific community but also was stimulating is called plasma cosmology. It has disappeared from labs and universities since the 1990s as a way of describing the universe, and we will see why. And now essentially survives in pop culture under the term electric universe. Electric universe proponents have in common their rejection of pretty much all the pillars of modern astrophysics, from relativity to a lot of observations that do not fit into their systems. It's a bit like a fancier version of flat earthers, fancier because they use plenty of complicated words. But if you have even a basic knowledge of physics and watch an electric universe video on YouTube or elsewhere, you will quickly realize that this is just mumbo-jumbo. It is like when the crew talks about physics and engineering in Star Trek. The words are there, it sounds like science, but it is just entertainment. The whole thing makes no sense because nothing is defined properly and there is barely any logical connection between propositions. But let's leave this aside, because initially plasma cosmology was an ambitious attempt at challenging cosmology in the 1960s, adopting a different angle. You know what plasma is in physics. It is a state of matter, a fourth state after the ones we are constantly surrounded with, solid, liquid and gas. A gas is typically made of molecules or individual atoms. A plasma is like a gas, but a gas of ions, that is to say atoms or molecules in pieces. They have had one electron stripped and 3 electrons surround them in the plasma. It takes additional energy to turn a gas into plasma. It has to be heated or subjected to a strong electromagnetic field. A property of plasma is that it is electrically conductive. It is full of free charged particles floating, so it can transport electric currents efficiently. So what did the concept of plasma cosmology mean, and why was there some pertinence to it? Because one of the question marks or problems of the modern standard model of particle physics and the theory of relativity is that they theoretically predict a similar quantity of matter and antimatter in the universe. In their language, a similar quantity of baryonic matter and antibaryonic matter, which is the same as matter and antimatter. The Big Bang should have produced a similar quantity of matter and antimatter too. But that is in theory, because in the observable universe, where is all this antimatter that, put in contact with matter, should mutually cancel themselves? It has never been found, and this is a bit embarrassing for all these models. The problem is called the matter-antimatter asymmetry, or baryon asymmetry. This question has never been solved, including today, and it was already on the table in the 1960s. One big advantage of plasma cosmology is that it provided a possible answer that would help support particle physics. Matter and antimatter would indeed be present in equal quantity in the universe, but they would be isolated in bubbles, gigantic pockets that would be separated by electromagnetic frontiers. This way they would remain separated, isolated, and avoid mutual cancellation. To get there, the proponents of plasma cosmology extrapolated to much bigger scales the properties of plasma that were being studied intensively since the 1920s. Now this theory could also integrate some of the observations made about the expansion of the universe. We would live with our galaxy and many others inside a pocket of matter, bounded with electromagnetic fields. But over time, similar pockets would tend to merge, like bubbles in water tend to come together to form a single, bigger bubble. That could be an explanation for the apparent expansion of the universe. In this approach, what we would see would just be the expansion of our bubble of matter. As you imagine, that would be a quite big change of paradigm in cosmology. The importance of gravitation at the scale of the universe would be strongly reduced. The age of the universe estimated by the Big Bang theory would no longer make sense, and standard theories about the formation of planets, solar systems, and galaxies would have it wrong, because they did not take into account the major role played by electromagnetic forces, according to the proponents of this theory. So this was an absolutely stimulating angle to look at cosmology, but quite quickly it appeared that this approach created more problems than it solved. First, it was based on many hypotheses that cannot be demonstrated or tested. Where are these separations between bubbles of matter and antimatter? They have not been observed directly, and indirectly neither. There are no known traces, light, radiations, signals of their existence. The assumption that plasma can carry electromagnetic forces on extremely large scales is also contradicted by experimentation. And there is also everything that works in particle physics and relativity. If these are wrong, why all the successful predictions they made? Because it cannot be a coincidence. Plasma cosmology doesn't provide an explanation to cosmic background microwave neither. So as the 70s, 80s and early 90s passed, it appeared more and more as an intellectual construction with little to support it. The argument that existing models are not fully satisfactory, which is true. None of the standard theories about matter and astrophysics in general explain everything on all scales. The lacks or the flaws of existing theories is no proof that any alternative is right, of course. This is why plasma cosmology and all its various ulterior iterations about the electric universe became fringe theories. They have actually never made a single cosmological prediction that could be verified, and they essentially exist as a discourse when standard theories have concrete applications that work every day. Particle physics is used in experiments all the time, or relativity serves to synchronize satellites in orbit around Earth, for example. At this point, you certainly understand why the Big Bang theory dominates today. Scientifically speaking, it defeated other possible cosmological theories, despite all its limitations. And the biggest limitation for the general public is that the Big Bang is a description of what probably happened, but it tells nothing about the why, what there could be before it, even though this question doesn't really make sense, because in the Big Bang theory's logic, time also appeared with the Big Bang, so it is absurd to wonder what there was before, if time didn't even exist. And the question of how it ends remains open between a never-ending expansion or, at some point, a contraction that would lead to a big crunch. So what happened in the early stages of the universe, according to the theory? It estimates that our universe appeared 13.8 billion years ago. For comparison, the age of Earth would be about 4.5 billion years. So our planet existed for about a third of the time the universe existed, based on these estimates. The first instance of the universe have been modelized, based on what we know of particles, energy, and how they should theoretically behave. But obviously there is no possible direct observation, and it is all very speculative. The universe would have appeared with a singularity, a name given to this original point because we don't have the models to describe it. Following the theory of relativity, it would have been a point of infinite density and temperature. In instants, far less than a second, the universe went through a quick inflation, a moment of still extremely high energy density and temperature, but now cooling down, and a phase of exponential growth, so fast and powerful that the universe could have expanded faster than light at the time. In these first moments, the laws of physics as we know them would have started to work, which is a necessary assumption to modelize this phase, otherwise we would have nothing to work with. Still, during the first second of its existence, the universe would have cooled down enough for the first particles to form, first quarks and gluons that combined to make protons and neutrons. And so the first bricks, the first components of atoms were born. But not the atoms yet. The universe was still too densely energetic for that. The first stages would have lasted seconds, but it took hundreds of thousands of years for nuclei of atoms and electrons to combine to form atoms. These atoms were hydrogen for the most part, the simplest and lightest kind of atom. You remember the cosmic microwave background that we mentioned repeatedly as evidence of the Big Bang. This is when it would have appeared. These newly born atoms were able to emit radiation, which since then continued through space unimpeded. This is how the cosmic microwave background appeared. After thousands of years, the universe was still very young. Matter was initially distributed evenly, but over time, slightly denser regions would have appeared. These denser regions attracted more matter because of gravitation. They grew denser and formed gas clouds that with more and more concentration formed stars, galaxies, and all physical astronomical structures observable today. So we have seen a lot of things since our departure, when we wondered whether we could go to the center of the universe. It turns out there is probably no such place, or at least this is what the current state of cosmology points to. But instead we have found a lot of information about how men have imagined, described, or measured this universe and their place in it, long before the birth of modern science. And maybe in 10 or 100 generations, our current understanding will look also very naive and lacking to our followers on Earth. For our first visit, we are going to leave the solar system and travel a few hundred light years, which is pretty close at the scale of the galaxy, to explore a fairly small but incredibly dense object, a neutron star, the closest one ever found. And I will also tell you about pulsars and magnetars. What is a neutron star? To understand it, we need to talk about the life cycle of stars. As you may know, it is believed, and there is strong evidence about that stars appear, live, shine for generally billions of years, and then they die, they disappear when they have exhausted the fuel they contained. When the fusion reactions between atoms that powered them is no longer sustainable. When this happens, the star does not slowly shrink and turns dark. It dies with glory, and the way it dies depends on its size, on its mass, and on its composition. A star about the size of the Sun, or a bit less, which is average in comparison with other types of stars, will tend to become a red giant, and what will remain of its core after that is called a white dwarf. But what does it mean? A red giant is what happens when the core of the star runs out of its main fuel, hydrogen, that for hundreds of millions of years it fused into helium. It is not like a switch that would suddenly be turned off. The phenomenon takes time. Hydrogen becomes rarer inside the core of the star, but the fusion reaction goes on, including in its upper layers. But the core is where hydrogen goes missing first, and when it happens, the core contracts because of gravity. This contraction makes it heat up. It becomes warmer than it already was. And in turn, this heats up the outer layers of the star. As a result, the star begins to grow, not in mass, but in volume. It occupies more space because the outer layers inflate. And this is not a marginal change. The star becomes gigantic compared with its past size, dozens of times bigger. For example, in the case of the Sun, it is expected to grow so much that it will reach the Earth's orbit when it turns into a red giant. But this is not the end yet, because inside the core of the star that has contracted and heated up, temperature and pressure have become sufficient to start fusing not just hydrogen, but heavier elements, especially helium, the product of hydrogen fusion. So, at this stage, helium atoms fuse, merge, into oxygen and carbon atoms. And for some time, the star keeps living on its stock of helium, until helium also runs out. And at this point, the end is near. There is no fuel left to burn that could keep the star producing energy. If you would like more explanations about that, you will find them in the story about nuclear fusion that I will link in the description. The general rule is that fusion of light atoms is exothermic. It makes energy available to be released because the new atoms need less binding energy. The bigger atoms are, the more likely they are to need extra energy to fuse, and so the reaction becomes endothermic. It needs energy available to be consumed to take place. This is why the fusion of heavy atoms cannot be a good fuel for a star, because instead of releasing energy, it consumes some. So, as fusion reactions die down in the core of the star, where carbon and oxygen pile up, the core expands again and cools down, whereas the outer layers of the star dissipate, and their matter forms what is called a planetary nebula, a cloud of matter floating in space. The core cools into what is called a white dwarf, a body where fusion reactions no longer take place. It is mainly made of carbon and oxygen, and it is much smaller than the original star. The Sun, for example, could end up having about the size of Earth, but a white dwarf is still very massive. Some of its matter has been shed and is now part of the planetary nebula. But a white dwarf produced by a star a bit more massive than the Sun could perfectly end up being as massive as the Sun is, while having the size of a planet. This very dense body is called a white dwarf because even though it no longer generates new energy with fusion, it is still intensely hot, and it keeps radiating, emitting energy. White dwarfs may still appear as very small stars, little shiny points with a faint light for billions of years. But eventually they should cool down and turn into black dwarfs, the dead core of a star that is now cold and no longer radiates light and heat. I said should, because the transformation of a white dwarf into a black dwarf is estimated to take a very long time, actually more than the 13 billion years that is the estimated age of the universe. So at this point, even the very first stars would not have had time enough to turn into black dwarfs. And if these estimates are correct, black dwarfs are objects that could, should start to appear in the future, in billions of years, but there are none yet. So that was the outcome of the death of a star that belongs to the same category as the Sun. It turns into a red giant, loses some of its matter, that forms a planetary nebula, and the core remains as a white dwarf. But as you see, the sequence of events in the late stages of the star's life depends on physical reactions that happen inside it. And these reactions depend on the mass of the star, its quantity of matter. What if the star is much bigger than that, 10 or 20 times bigger, more massive than the Sun? A giant star. In this case, the core of the star is also much bigger, and this means that the gravity, the gravitational force, and the heat inside the core are going to be higher. So high that fusion reactions can go on after the disappearance of hydrogen and helium, because there is enough energy available. These giant stars go through the same process of exhausting their hydrogen reserves. Then they fuse helium atoms, and turn them into carbon and oxygen. But at this stage, their mass is enough to fuse carbon into heavier elements: neon, silicon, sulfur, iron. And only once these elements, especially iron, form the core of the star, it can burn no more. With the extinction of fusion reactions comes a collapse. As fusion reactions no longer push outward, the star's core suddenly collapses on itself due to gravity, and it becomes so tightly packed that even subatomic particles like protons and electrons merge. In other terms, the gravitational force is enough to overcome the resistance of atoms. As you know, there is a lot of void inside atoms, a lot of distance between the nucleus and the cloud of electrons around it. The sudden disappearance of this void makes the core shrink dramatically. A star's core the size of Earth can shrink to a ball with a radius of just a few miles. And in this core, subatomic particles have merged. As you know, a distinction is usually made between 3 different types of particles inside atoms. There are protons and electrons, which each have opposite electric charges, and neutrons, which have no net electric charge. In reality, protons and neutrons are themselves made of smaller particles, but we don't need to go into that for tonight. The mergers of protons and electrons form only neutrons, and the atomic organization of matter disappears. The core turns into a dense pile of neutrons, where, due to this sudden compression, temperature rises to inconceivable levels, billions of degrees. the outer layers of the star are suddenly pulled into it, which crushes it even further, and the sudden accumulation of energy cannot be contained. So the core explodes, and happens what is called a supernova, an explosion that sends a powerful shock wave in space and disseminates large amounts of matter, of material, into space, especially these heavier atoms like iron and others that have just been produced by fusion reactions from gold to uranium. It is believed that all these elements that are present around us and including inside our bodies in small quantities must have appeared and been disseminated by a supernova of this kind billions of years ago, before the formation of the solar system. And when our system formed, it reused some of this matter that had been transformed in the last moment of an extinct star system that disappeared before the solar system began to form. So finally we are getting there. What remains of a giant star, above 8 to 10 times the Sun's mass, can form a neutron star, which is actually smaller than a white dwarf, but much denser. Inside a white dwarf, gravitation is not enough to break the resistance of atoms. So a white dwarf remains made essentially of carbon and oxygen. The elements remain distinguishable, whereas inside a neutron star, there are no longer distinguishable elements, just a mass of neutrons, because as we saw before, electrons and protons have merged. So typically a neutron star is 1,000 times smaller than a white dwarf, but with a similar mass and sometimes a bigger mass. Neutron stars are like an intermediary body between white dwarfs and black holes that we will talk about later. If the giant star is not 10 or 20 times more massive than the Sun, but 50 or 100 times or more, the collapse of its core may theoretically create an even denser black hole. It is believed that neutron stars can appear when stars that are at least 8 to 10 times more massive than the Sun, and up to about 25 times the Sun's mass, end their life cycle. Below 8 times, a white dwarf is more likely, and above 25 times, a black hole. But it is not that systematic, because the mass is not the only factor. The richness of the star in metal can be one too. We will visit a black hole later, but for the moment, let's talk about neutron stars and the different forms they can take. First, white dwarfs are probably much more common than neutron stars. It is estimated that 97% of stars are not big enough to form a neutron star, and only an even smaller fraction are supergiants that can leave a black hole when they die. This state of matter, where there are only neutrons, results from a kind of equilibrium. Pressure, gravitation, is strong enough to compress matter to the state of neutrons. But on the other hand, there are forces that prevent further collapse, forces that protect the integrity of neutrons. These forces are called neutron degeneracy pressure and repulsive nuclear forces. we don't need to go further into these forces. Let's just bear in mind that they resist, they counterbalance gravitation and stop the collapse. But this works up to a point. Theoretically, a neutron star can have up to twice the Sun's mass, above about 2 times. This is just an estimate, and it is still discussed between physicists, because different forces are at play, and their sum, their interaction is complex to estimate. But it gives an order of magnitude. So above 2 times, the collapse process could not be stabilized, and further collapse of the core of the body on itself would happen. Further compression would make a black hole appear. A black hole with still the same mass, but occupying an even smaller space, and in which even neutrons have disappeared. But we will come back to that. Still, even though they are not black holes, neutron stars have a density that is hard to imagine. The mass of a star like the Sun, contained inside a body that is just a few miles across. This means that a little bit of neutron star material contains an extraordinary quantity of matter. To take an example, the bodies of all humanity, all 7 or 8 billion people, compressed like that, could fit into a matchbox, and there would be some space left in the box, because precisely a matchbox of neutron star material would be estimated to weigh about 3 billion tons. Gravitation at the surface of a neutron star would be around 200 billion times what it is at Earth's surface. This is inconceivable. And another consequence of this enormous mass in a small space is a strong magnetic force, a powerful magnetic field that surrounds the body. I will also link another story for more explanation about what magnetism is, how it works, in the description. But these powerful magnetic fields are important because they are organized around 2 poles, like the Earth's magnetic field, but billions and billions of times more powerful. A magnetic axis exists between these 2 poles, and the magnetic fields may funnel jets of particles out along the 2 magnetic poles, so a beam of radiations can come out of the pole. And another characteristic of neutron stars is that they rotate very fast on their axis. They rotate fast because the much bigger star they were born from rotated, and when it disappeared, the core kept this rotation, but it is much smaller, so the rotation rate measured at the surface became much higher. In physics terms, there is a conservation of the angular momentum, but you can easily picture it imagining a figure skater doing a spin. When they are spinning, their rotational speed can accelerate if they draw in their arms. It is not an acceleration due to an additional effort, it is because drawing in the arms decreases the inertia, the moment of inertia, and mechanically it makes them rotate faster. This is what happens on a different scale when the star's core collapses to become a neutron star. The radius suddenly diminishes, But as the angular moment remains constant, the rotation accelerates. So typically a neutron star rotates on its axis in a matter of seconds or even milliseconds, extremely fast. Now, when you combine these radiation beams coming out of the magnetic poles and the fast rotation, you get what is called a pulsar. Seen from afar, like from Earth, or more exactly observed from Earth with instruments, because pulsars are not visible to the naked eye, and instruments are necessary to detect their beams of radiation. So, seen from afar, a pulsar is like a lighthouse that would rotate very fast. Each time the beam points at the observer, a signal is perceptible, and this signal repeats very regularly. It follows the neutron star's rotation. Pulsar means pulsating radio source, and thanks to this signal that they repeat very regularly, thousands of them have been identified in our galaxy alone. This is only a fraction of existing pulsars, probably, given the number of dead stars in our galaxy. I told you earlier that the majority of stars are not massive enough to leave a neutron star behind. But there are billions and billions of stars in our galaxy, so that still leaves hundreds of millions that are big enough to turn to a neutron star and become a pulsar. A particular and less frequent type of neutron star is called a magnetar, because they have an extremely powerful magnetic field. They are not necessarily bigger than other neutron stars. As we saw, their mass cannot exceed 2 solar masses, otherwise they collapse further. But their magnetic field is particularly powerful, and they tend to rotate slower than pulsars, typically one every 2 to 10 seconds. Magnetars have been identified separately from pulsars, because they are responsible for bursts of rays that were detected from different parts of our galaxy. And they became the best explanation for that phenomenon. As of 2021, 20 to 30 magnetars have been located in the Milky Way. Not many in comparison with the thousands of pulsars. But this is because magnetars have a short lifespan. Their magnetic field decays quickly, in a few thousand years, and so they become less active and detectable. So there are probably millions of inactive or less active magnetars in the galaxy, and only the youngest have been spotted, the ones that produce spectacular bursts of rays. At this point, we have seen what happens to stars the size of the Sun, a bit less or up to 7-8 times the Sun's mass. What happens to giant stars, the ones that tend to turn to neutron stars, up to about 25 solar masses. But what about supergiant stars that are more than 25 times bigger than the Sun? In their case, the collapse of the core on itself does not end in a pile of neutrons. The neutrons themselves are crushed and cease to exist as such. They form a body whose gravity is so strong that nothing, including the fastest particles or rays in the universe, can escape it if they come close enough. Very dense objects, like neutron stars, may have a very strong gravity. But this is not enough to capture light, for example. To understand it, we need to talk about the concept of escape velocity. When we are on Earth and we throw something at the sky, it falls back, a little bit because there is friction with the air. This may slow the object down as it rises, but if it falls back, it is because the gravitational pull of the planet attracts it back to the ground. The more energy, the more velocity what we throw has, the higher it can go before falling down. A basketball thrown by hand will rise a few meters. The bullet from a gun can go higher. But this is still not enough to escape the planet's gravity. To escape it, you need to either provide more thrust as the object rises. For example, a rocket. When a rocket traveling to space takes off, additional push is provided for several minutes as it burns its fuel reserves. And this is how it can free itself from the Earth's gravitation. Or you need to give the object enough push, enough initial speed, that the planet's gravity will not be sufficient to stop it from escaping. This is the concept of escape velocity, the minimum speed necessary to break free from the gravitation of an object with a mass. It depends directly on the object's mass and the distance of your starting point from the center of this mass. For example, the escape velocity from Earth's surface is about 25,000 miles per hour. That's 40,000 kilometers per hour. Man-made ships do not reach this speed, and rockets manage to escape despite lower speeds only because they have a continuous thrust during their ascension. Bodies or particles in space don't have that self-propulsion. They receive some kinetic energy that they don't lose as long as they don't collide, but they don't accelerate by themselves. So, the more massive the body you try to escape is, the fastest you need to go. And this concept was understood long ago, in the 18th century, with the elaboration of the theory of gravitation. And soon, this theoretical development led to a theoretical question. What if an object was so massive, with such a strong gravitational pull, that its escape velocity was higher than the speed of light itself, the speed of light being the highest conceivable speed, at least based on our current understanding of physics? Then, in that case, nothing, not even light, could escape such a body. This is the concept of a black hole. A body so massive, which doesn't mean so large, matter is so compressed inside of it that a black hole does not need to occupy a lot of space, but a body so massive that once something has been captured by its gravitation, no escape is possible. Or, at least conceptually, no escape without self-propulsion. This is why they are called black holes. Black because not even light can escape them, and you can literally fall into them. But the term hole can be a bit misleading because they are very, very dense, the opposite of a void. for an astronomical black hole to form. A mass of at least 2.5 to 3 times the Sun's mass is necessary. Below that, the mass is not enough for the core of a star to keep collapsing on itself. But if 3 solar masses is the lower limit, you may wonder why there are stars that are dozens of times more massive than the Sun, and yet they don't turn to black holes. This is because as they burn their fuel during their life, other forces compensate for gravitation and prevent the star's core from shrinking. It is when these reactions die down that what is left of the star, the core, can finally collapse on itself, and if it is massive enough, turn into a black hole. Black holes are sometimes pictured as irresistible vortexes that will swallow anything. This is true if you come too close to them, but their gravitation, their impact on other bodies, is not more powerful than other objects of a similar mass. A black hole with 5 solar masses has the same gravitational pull as a star with 5 solar masses, and there are plenty of them. So black holes can have satellites, they can capture other bodies with their gravitation, but it doesn't mean they will end up swallowing them if these bodies are far enough and have their own speed. If this is the case, the captured body will keep its distance with the black hole. It will stay on an orbit around it. The limit, the point of no return of a black hole, is called the event horizon. Beyond that frontier, beyond that limit, there is no escape left. But as long as it is not passed, a high enough velocity will allow fast particles to escape like light. This is why, visually, the event horizon would be like the limit, the boundary of the black hole. Everything beyond it is dark because light cannot escape. I will leave the physics of what happens inside a black hole for another time. This topic is complicated and still discussed between physicists, in particular because it is believed that at the center of each black hole there is what is called a singularity, a point where gravitation becomes infinite, and there is no theory at this point that can model or describe this phenomenon. But if we keep an external look, a lot of discoveries of black holes have taken place in the past few decades, and 2 main groups are identified. There are stellar mass black holes, the ones that form when large star cores collapse under their own weight, and there are supermassive black holes, the ones that are believed to be at the center of galaxies and have much higher masses, billions of times the Sun's mass. The origin of supermassive black holes is poorly known, but what is likely is that black holes can grow. They can absorb more matter, capturing objects. They can merge, including supermassive black holes when galaxies collide. And as you may have seen, the first pictures of black holes were released. What we see on them is obviously a black spot, but it is contoured by light. And this sounds paradoxical. I just told you that black holes did not let light escape, by definition. So why would there be like a visible ring around them. What we actually see, and this is an illustration of Einstein's theory of relativity, is an effect of the black hole on its environment. The definition of gravitation, according to Einstein's theory, is that massive objects affect others because they curve, they warp the space-time, the fabric of the universe. The bigger the mass, the stronger the warping, the curvature. And this curvature does not only affect objects which also have a mass, as Newton's initial theory supposed. It affects everything, including light, which is without mass. The ring of light that we see on these pictures is not emitted by the black hole. It would come from the effect of the black hole on its surroundings, where space-time is warped, and this affects the path of visible light, allowing us to see something. There would be much to say about black holes, but we have more things to see in our cruise, and space oddities are not limited to what stars turn into when they die. We have seen that black holes could be extremely massive objects, and as such contain a big chunk of the matter that exists in the universe. Maybe the majority of it. Or do they? Let's talk about dark matter, a hypothetical form of matter whose existence has never been directly proven, but that could represent around 85% of the matter in the universe, if it exists. What is this, and why is this hypothesis seriously considered? To understand it, we need to go back to the 20th century, when astrophysics and observation of faraway galaxies made giant leaps forward. At the time, the theories of gravitation and Einstein's theory of relativity were already well known and accepted as valid by the scientific community. But a number of observations did not really fit them. In particular, the observation of galaxies and how they move in space, the observation of their motion. It was observed that galaxies could travel away from each other, and this was an important step in realizing that the universe was in constant expansion. Galaxies also are big masses that interact with each other via gravitation, even though they can be far apart. But the mapping of the universe, at least what we can see of it, soon revealed that something was off. Many galaxies did not behave as they should have, based on their estimated mass and the laws of gravitation. But the laws of gravitation cannot be thrown away easily. They work, and their predictions have permitted many discoveries, including planets that were guessed before they were observed. So if gravitation was not the problem here, it had to be the mass of these galaxies that was not correctly estimated, and sometimes widely so. Some galaxies should have been more than 10 times more massive than they seemed to be, to explain their influence, their interactions. This was the unexplained mystery that gave birth to the hypothesis of dark matter. Dark because it is undetectable as of today. Not only visually, but also because it seems to not interact with the electromagnetic field which means it does not absorb, reflect, or emit any radiation. And so it could be of a different nature than the matter we know of. Its only shared property with familiar matter would be that it has a mass. This is why dark matter is speculative. It is deducted from our inability to explain observed phenomena. The motion of galaxies is not the only clue that points to its existence. There are other lines of evidence, such as the formation and evolution of galaxies, or the measurement of what is called the cosmic microwave background, a radiation that is a remnant from an early stage of the universe. That makes a lot of unexplained phenomena that could be explained by the existence of dark matter. The problem is that no one has ever observed it, assuming it exists. All about it is hypothetical. Its only interaction with known matter would be through gravity, but we have no idea of its possible nature. Are these gigantic but undetectable masses, or a few particles with enormous gravitational force, or something we have not managed to conceive? The primary candidate today would be a kind of unknown subatomic particle, unknown as of yet. The strength of this hypothesis is not just because the existence of dark matter would avoid having to throw away the gravitation theory, which would be very uncomfortable. It is also that its existence can be deducted from various independent approaches, as I said before. Solving the problem raised by one of these approaches with a different explanation than dark matter would be a thing. But solving all of them looks very difficult. And for that reason, even though it is unobserved, elusive, and at the same time would be expected to make the bulk of matter in the universe, this hypothesis is still the one favored by the scientific mainstream. That's an ongoing mystery, and it is humbling. If dark matter is real, it means that at this point we barely know about 15% of the matter in the universe, and the rest escapes our perception so far. But if it does not exist, it is maybe worse. It means that large parts of physics fall down, and we become unable to explain a lot of observations that have been repeated many times and look solid. Until now, in our crudes, we have been looking at large-scale objects or phenomena. But on a smaller scale, at the scale of planets, there could also be bodies that can theoretically exist and would challenge our knowledge of planets. Our knowledge of planets being primarily based on the observation of the solar system. We have two big types of planets in our system. There are rocky or telluric planets with a metallic core. It is believed because heavier elements tend to migrate to the core in their formation process. And around this metallic core, they have a rocky envelope where the dominating elements are silicon, oxygen, hydrogen, and to a lesser extent, plenty of other elements in smaller quantities. And then there are giants, planets with probably a metallic core too, but around it, layers of gas. And these ones are divided into gas giants, when they are mainly made of hydrogen and helium, like Jupiter and Saturn, and ice giants, when they contain more astronomical ices, like water or ammonia, like Uranus and Neptune. But the solar system is just one system among billions, and nothing says that other types of planets do not exist. Planets with a different structure or a different composition. This is all speculative, but theoretically possible. And now we are going to review different types of planets that may or may not exist somewhere in the universe, like coreless planets, carbon planets, planets covered by oceans, or orbiting around a black hole. The concept of a coreless planet is not a hollow planet. Hollow planets were imagined in different contexts, including in fiction along history. But given what we know about the universe, it looks impossible for a hollow planet with just a shell to form. There is no reason for a void to exist inside, at least not naturally. A coreless planet would be a rocky planet without a metallic core, a terrestrial planet that would just be a giant rocky mantle. The formation models take into account the type of material available when planets form around a star, and there is a lot of metal in this material, especially iron. As we saw before, when I told you about the appearance of new heavier atoms in large stars when they reach their last moments, iron is a frequent outcome of fusion reactions, and for that reason it is relatively abundant. So a rocky planet without a lot of metal and a metallic core is hard to conceive. If we look at the solar system, we even have an example of almost the opposite, with the case of Mercury, which has a big metallic core proportionally and a small rocky mantle. But the formation of a planet made primarily or mostly of rock material is not unthinkable. It would theoretically be possible in cooler regions of a system far from the star. A first mechanism would be when the planet accretes far from the star in a colder environment. Accretion means the progressive absorption of material on its orbit by gravity. And in that case, it would happen in an environment where metallic iron is bound into silicate material crystals. In other words, iron would be trapped into rock structures that will not melt and will not let it escape. In that case, the formation mechanism would not allow metal and rock to be separated and the planet to differentiate, that is to say, to have a core and a mantle with different compositions. Another possibility would be that the planet accrete from water-rich and iron-rich material, also slowly enough and far enough from the star for water and iron to react and form iron oxide, rust, before differentiation of a metal core has taken place. In that case, provided iron droplets are mixed enough with the other elements, iron could stay entirely trapped in the mantle and no core could form. Maybe we have already detected coreless exoplanets, and we don't know it because apart from their internal structure, their sizes are expected to be similar to planets with a core. They would form far from the star based on models, but this does not exclude the possibility of a migration within a system, so they could move to a closer orbit later. The opposite to a coreless planet would be an iron planet, a type of planet with a metal core and little to no mantle. Mercury is almost one, and that is proof enough that metal planets, or almost metal-only planets, are a possibility. The formation process here could be different. These planets are expected to form near the star, because this is where the concentration of iron-rich material would be found when a new star system appears. They could form naturally with mostly metal, but like it is hypothesized for Mercury, they could appear after collisions. A regular terrestrial planet would form, and later, large collisions with asteroids would strip it of its mantle that would be ejected into space and lost. So the iron planet, in that case, would be the remaining core of a rocky planet that has been exposed and has cooled down. A consequence of being a metal planet is that there could be no plate tectonics or volcanism, just different layers of metal with a colder solid outer layer and a hotter core where metal is melted. Yet another type of theoretical planet with a different composition would be a carbon planet. Not a planet made only of carbon, but one where there would be more carbon than oxygen. What does it mean? Rocky planets in the solar system, like Earth, Venus, Mars, formed in an environment where there was more oxygen than carbon, almost twice more. Their carbon to oxygen ratio is around 0.55. It means that in terms of mass, Earth, for example, has a bit more than 2 pounds or 2 kilograms of oxygen for 1 pound or kilogram of carbon. What we call rock are compounds made mainly of silicon and oxygen, silicates. This seems to be the norm, because oxygen is more abundant than carbon in the universe. Oxygen is the third most prevalent element, after hydrogen and helium, whereas carbon comes in fourth. But we also know that all star systems don't have the exact same carbon to oxygen ratio. Some are richer in carbon than ours. For example, exoplanets have been detected with a higher carbon-oxygen ratio, as high as 0.78. And so there could be planets which would look like Earth in terms of size and internal structure, but the domination of carbon over oxygen, or a parity, would mean chemistry and climate at their surface would be very different. the equivalent of geologic features on Earth may be present, but with different compositions. For example, instead of being composed of liquid water, the rivers might consist of oils. If the temperature is low enough, gases in the atmosphere may synthesize into hydrocarbons that could rain onto the surface. And the surface would be expected to look dark and reddish from hydrocarbon deposits. Yet another type of planet, not because of its composition, but the object it orbits, could be so-called Blanets with a P like black, planets that orbit a black hole. This is more than purely theoretical, it is likely to exist, even though none has been detected yet. Blanets would be fundamentally similar to planets and could be of different kinds, and they could be located around supermassive black holes. It is a bit more difficult to imagine them around a black hole born from the collapse of a big star, because even though this supergiant star probably had planets, it went through a supernova that destroyed the system or expelled its planets. It is not completely impossible, though, because planets could be captured later, once the black hole exists. We know that there are rogue planets that escaped the system where they formed, and some of these rogue planets may even travel between galaxies. But a supermassive black hole at the center of a galaxy is a better candidate because it could capture many of these planets, and even more because there is an accretion disk around such black holes, a region with enough material in orbit to form new bodies, possibly thousands. There is a safe zone around such black holes, where satellites can exist, a zone where they are close enough to be captured by the black hole's gravitation, but far enough for an equilibrium to form between their speed and the black hole's pull, so they can adopt and stay on an orbit. These are different types of terrestrial planets that could be markedly different from the ones we know. But gas giants could also be different. The ones we have in the solar system are quite distant from the Sun, but we know that there are giant gas planets that orbit closer to their star. This is what is called a hot Jupiter, hot because of the proximity to the star. And when this happens, they could become something called Chthonian planets, gas giants that would have been stripped of their gas layers by the star, leaving only their solid core that would look a lot like a terrestrial planet. Or there could be helium planets. On Jupiter and Saturn, hydrogen is the main component, and helium is the secondary one. A helium planet would be one where helium dominates, and they might form in a variety of ways. The first possibility would be if hydrogen evaporates. If the planet orbits close to the star could drive off lighter gases more effectively, and hydrogen is lighter than helium. So, over time, hydrogen could be depleted and leave helium as the primary component of the planet. Another type of planetary object with a layer of helium, rather than a planet, could appear from a small white dwarf, you remember what white dwarfs are. We spoke about them at the beginning. They are the remnants of sun-sized stars, after they turn to red giants when they exhaust their hydrogen reserves. Now, in a binary system, a system with two stars, where both have passed their main sequence and died, turning into white dwarfs, one may have lost so much of its mass that it approaches planetary mass, and it orbits around the larger white dwarf. The planetary nebula left by the stars would be rich in helium, and this smaller white dwarf may be surrounded by layers of gas dominated by helium, making it look like a gas planet, even though technically it used to be a star before, which is why it would be called a planetary object rather than planet. We are approaching the end of our cruise, and it is now time to return to Earth after this little exploration journey. As you see, space is still full of wonders, unsolved mysteries, and phenomena that wait to be discovered or understood. For now, you can close your eyes and let yourself go to a sweet, restful sleep. Sleep well. Sweet dreams. Au revoir.